If you're having trouble falling asleep, or you just want to relax, you're in the right place. Have you ever wondered what secrets lie hidden in the dark corners of our solar system? From raging storms that could swallow entire planets to mysterious moons that might harbor alien life, the cosmos is far more terrifying and fascinating than you might think. In this video, we're counting down 100 scary and interesting facts about the planets that orbit our sun. Strap in for a journey through scorching heat, freezing darkness, crushing pressure, and bizarre alien worlds. You'll never look at the night sky the same way again. Ready to explore the terrifying wonders of space? A world of furnace and freezer, Mercury endures the most extreme temperature swings in the solar system. Daytime on the sun-blasted side reaches about 430 degrees Celsius, hot enough to melt lead, while the airless night side plummets to minus 180 degrees Celsius. With no atmosphere to buffer heat, a person standing on Mercury would face lethal conditions in the near vacuum. Bodily fluids would boil off in seconds, and the 600 degrees Celsius temperature plunge between day and night would flash freeze what remains. Ice in eternal shadow. Despite its hellish days, Mercury hides water ice in places the sun never reaches. Deep inside polar craters, where sunlight never penetrates, radar observations and spacecraft data have confirmed thick deposits of frozen water. These reservoirs lie in perpetual darkness at temperatures around minus 200 degrees Celsius, preserved for eons. It's a haunting thought. Airless Mercury, closest planet to the sun, harbors patches of eternal frost in the black depths of its polar craters. A double sunrise. Mercury's rotation and orbit produce bizarre sunrises. The planet spins 3 times for every 2 orbits around the sun, so a single solar day lasts 176 Earth days. At some longitudes, as Mercury nears the sun appears to rise, then reverse and set briefly, only to rise again and continue its journey. An observer would see dawn break, the sun peak above the horizon, then strangely sink back down before rising once more, a consequence of Mercury's highly elliptical orbit and slow spin. A full day, night cycle on Mercury spans 2 mercurial years, meaning if you lived there you'd celebrate 2 birthdays before seeing another sunrise. Black sky, blazing sun. Under Mercury's blistering sun, the sky remains pitch black, with virtually no atmosphere. Even midday looks like space. Stars shine even at noon. The sun looms over 3 times larger in Mercury's sky than on Earth, and sunlight is about 7 times more intense. A human explorer would face a gigantic, blinding sun in a dark sky, a stark, almost surreal vault of blackness lit by a fierce white orb. Mercury's comet-like tail. Mercury has almost no atmosphere, but it does have a ghostly exosphere. Atoms knocked off its surface by solar wind. Solar radiation pushes some of these atoms, especially sodium, into a long tail, stretching millions of kilometers behind Mercury like a comet. If you stood on Mercury's night side at dawn, you'd see a faint orange glow along the horizon, sodium gas fluorescing like neon and streaming away into space. This ephemeral tail, invisible to human eyes but detected by instruments, is Mercury slowly evaporating under the sun's bombardment. The iron heart. Mercury is essentially a giant metal ball with a thin, rocky shell. Its iron core makes up about 85% of Mercury's radius, far larger proportionally than Earth's core. This suggests a cataclysm in Mercury's past. Perhaps an ancient mega-impact stripped away much of its original crust and mantle, leaving an iron-heavy remnant. Mercury today is like a planetary iron heart, the product of cosmic violence early in the solar system's history. Seismic data and orbital measurements confirm the core is partly molten and dynamic, even generating a weak magnetic field. Shrinking and wrinkling. Mercury is not a dead ball of rock, it's actually shrinking. As its hot iron core slowly cools, Mercury has contracted over billions of years by up to approximately 14 kilometers in diameter. The surface has buckled, pushing up great curved cliffs, lobate scarps that can run hundreds of kilometers long and over a kilometer high. These giant wrinkles resembling thrust-fought scarps are Mercury's skin crinkling as the planet cools and contracts. Some faults cut across relatively young terrain, suggesting Mercury is still shrinking today, geologically speaking. Weird terrain from a planetary punch. One hemisphere of Mercury bears a bizarre patch of jumbled hills and troughs known simply as the weird terrain. This chaotic region sits directly opposite the colossal Caloris Basin, a 1,500 km-wide impact crater formed by a devastating asteroid strike. When the Caloris impact occurred, shock waves traveled through Mercury and converged at the antipode, shattering and heaving the crust into a strange disrupted landscape. Walking there would be haunting. The ground is a riot of hills, ripples, and hollows frozen in place by one titanic blow that rang Mercury like a bell. Magnetic tornadoes. Mercury is the only inner planet besides Earth with a global magnetic field. But Mercury's is crumb weak, about 1% the strength of Earth's. And it's no gentle shield. Mercury's magnetosphere is so small and buffeted by solar wind that it develops leaks. NASA's MESSENGER probe found twisted magnetic flux tubes connecting Mercury's field to the Sun's, essentially magnetic tornadoes, 800 kilometers wide, funneling solar plasma to the surface. Through these temporary magnetic portals, hot solar wind plasma blasts directly onto Mercury's surface. Mercury's tenuous atmosphere is continually replenished by this process, as solar wind particles sputter atoms off the soil and into the sky. The result is a dangerously dynamic environment, as if invisible tornadoes of magnetism intermittently scour the landscape. Ice and fire paradox. In 2011, NASA confirmed that water ice lurks at Mercury's poles, protected in permanent darkness. At the same time, Mercury's day side can be hot enough to glow dull red. This stark contrast means a stranded rover could theoretically drive from a region cold enough to preserve ice for billions of years into an inferno capable of melting lead in a matter of days. Mercury is a planet of extremes. It can simultaneously boast some of the solar system's highest temperatures and lowest natural temperatures on its surface. It's a world where frost and fire coexist, a truly unsettling concept. Spin-orbit resonance. A day twice as long as a year, Mercury's rotation is locked in a 3-2 resonance with its revolution around the Sun. This means Mercury rotates on its axis exactly 3 times every 2 orbits. The consequence is that one Mercurian solar day lasts 176 Earth days, 2 full Mercury years. An observer on Mercury would find that from one noon to the next takes about 6 Earth months. If you started a day on Mercury at perihelion, closest approach to Sun, you'd see the Sun rise, perform its bizarre dance, rise, reverse, rise again, and finally set 88 Earth days later, only for the Sun to not rise again for another 88 days. For half the Mercury year the Sun is gone, plunging the land into an airless, frigid night. It's a day-night cycle so long and eerie that it defies earthly intuition. Fading into starhood, Mercury's orbit is so deep in the Sun's gravity well that it helped prove Einstein's theory of relativity. The perihelion of Mercury's orbit drifts by 43 arcseconds per century due to space-time curvature. Some far-future simulations suggest that chaotic perturbations in the inner solar system could even cause Mercury's orbit to destabilize on billion-year timescales. There's a 1% chance that Mercury could eventually be thrown into the Sun or out of the solar system, or even collide with Venus or Earth, though these scenarios are extremely far in the future. While low probability, Mercury's long-term fate remains a subject of existential intrigue. The tiny planet might not be a permanent fixture of the solar system over cosmic timescales. Mercury is alive, geologically. Once thought long dead, Mercury shows signs of recent geological activity. MESSENGER discovered hollows, bright, shallow depressions with bluish tints that appear to be fresh and still forming today. These hollows likely form when volatile elements within Mercury's crust, like sulfur, sublimate or outgas under the harsh solar bombardment, causing the rock to crumble into dust and leaving behind pit-like scars. Some hollows are on the order of only tens of meters deep and seem to lack superposed craters, implying they're geologically young. Mercury, it appears, is still evolving even now. Intense sunlight and solar wind might be eating away at parts of Mercury's surface, etching spooky new hollows on a planet once presumed geologically inert. A relic of violence. Everything about Mercury, its oversized iron core, its slow spin, its sparse rocky mantle, suggests it is a survivor. One leading theory posits that Mercury began as a larger world, but an early giant impact tore away much of its original crust and mantle. The calamity left a metal-rich body that is essentially a planetary iron core wrapped in a rocky rind. In a sense, Mercury is a planetary corpse, the skeletal remains of a protoplanet that was gutted by catastrophe. As we study Mercury, we're reading the gruesome aftermath of an ancient world-shattering collision, one so violent it stripped a planet to the bone. Venus. Hellish twin, often called Earth's sister Venus, is in fact a lethal hellscape. Its thick, CO2-rich atmosphere creates a runaway greenhouse effect, baking the surface to 465 degrees Celsius, 869 degrees Fahrenheit, hotter than Mercury, despite being farther from the Sun. The pressure at Venus's surface is 92 bars, equivalent to being 900 men 0.6 miles under Earth's ocean. Any spacecraft or person on Venus is crushed by an atmosphere as dense as water and broiled by heat high enough to melt lead. The Soviet Venera landers that touched down in the 1970s and 80s survived only minutes before the supercritical CO2 atmosphere, neither true gas nor liquid, destroyed them. If you could stand on Venus, you'd experience a pressure cooker environment and temperatures that can melt metal, truly hell on a planet. Acid shrouds and eternal dusk. The skies of Venus are perpetually hidden by thick yellowish clouds of sulfuric acid. Sunlight struggles through this toxic haze, leaving the surface lit in a dim amber gloom. It even rains sulfuric acid, but strangely the acid rain evaporates before reaching the ground due to the intense heat lower in the atmosphere. This phenomenon, called virga, means the Venusian surface never feels a drop of rain. Instead, acid clouds simply vanish into acrid steam above the superheated ground. Standing on Venus at noon would feel like twilight. A wan orange light filtering through the dense cloud cover, with the sun never directly visible. It's an oppressively overcast world with a sky that drips acid from above but never touches the ground. Backwards and slow, Venus spins backwards retrograde relative to most planets, and incredibly slowly. A single Venus day-night cycle lasts 116.7 Earth days, the time from one sunrise to the next. In fact, Venus's sidereal day, 243 Earth days, is longer than its 225-day year, and the sun rises in the west and sets in the east. If you could endure on Venus's surface, you'd see a bizarre spectacle. The sun would rise from the wrong direction and creep across the sky so slowly that it takes nearly 4 months to set. Venus's languid rotation means its day is nearly half an Earth year long. Combined with the eternal cloud cover, time on Venus's surface loses meaning. The sun's motion is imperceptibly slow behind the toxic clouds. Lightning in the inferno. Venus's atmosphere isn't just hot, it's volatile. Soviet Venera probes and orbiting spacecraft detected crackling radio emissions indicative of lightning within the clouds. Gigantic lightning bolts flash in Venus's dense clouds, igniting chemistry that produces substances like carbonyl sulfide. These lightning storms likely feed the mysterious glow known as ashen light, a faint illumination of the night side reported by observers for centuries. One hypothesis is that Venerian lightning creates a dull airglow on the dark side. So while the ground sits under perpetual dim daylight, the sky above is alive with unseen electrical fury, with thunder echoing through the dense air. Venus in its own way has storms as fearsome as Jupiter's, but hidden behind its veil of acid. The ashen light mystery. Observers as far back as the 17th century claimed the dark side of Venus sometimes faintly glows. This ashen light is an eerie, elusive phenomenon. a subtle coppery illumination on Venus's night hemisphere. It has never been conclusively photographed and remains unconfirmed scientifically, leading some to suspect it's an optical illusion. Yet Soviet spacecraft did detect unusual oxygen emissions that could cause a gentle night glow. One theory posits that airglow or lightning in Venus's atmosphere might create a dim night-side glow visible to vigilant observers. Imagine standing on Venus's dark side. The landscape might be lit by a faint ghost light from the sky, a diffuse glow in the utterly cloudy night. Whether real or imagined, the ashen light adds to Venus's mystique as a world of subtle horrors. Snow of metal. Venus's mountains are topped, not with ice, but with metallic frost. Radar reflections from the highest peaks, like Maxwell Monte, indicate a bright material coating them. Scientists believe that lead and bismuth sulfides condense from the atmosphere at cooler high altitudes, forming a shiny metallic snow that dusts the mountaintops. In Venus's bizarre climate, it literally snows heavy metals. Climb a Venusian peak, and you'd find the rocks coated in a toxic silvery glaze of galena and bismuthinite, a far cry from the water ice snows of Earth. It's a scene out of science fiction, dark mountains glittering with leaden frost under an orange sky. Pause. Crushing atmosphere of supercritical CO. The atmosphere at Venus's surface is so dense and hot that carbon dioxide exists in a supercritical state, a phase of matter that is neither true gas nor liquid. In this supercritical fluid, CO penetrates pores and dissolves materials in ways that defy earthly intuition. Sound would travel far faster than on Earth, and with strange fidelity in this thick medium. A human on Venus with appropriate cooling and pressure protection would find that the air feels almost like a liquid in its thickness. If you waved your hand, you'd encounter significant drag. Venus's air isn't the thin gas we're used to. It's an almost ocean-like fluid of oppressive CO. It's an environment more akin to deep-sea diving than strolling under open sky. Volcanoes, past and present. The surface of Venus is covered in volcanoes and vast lava plains, and much of it is geologically young, average surface age approximately 0.5 billion years. This suggests that Venus underwent a planet-wide volcanic resurfacing in the relatively recent past. Radar imaging shows 1,600 plus major volcanoes, and there is strong evidence that volcanic activity persists today. In 2020, astronomers announced surface changes, a volcanic vent that expanded and changed shape over an 8-month span, indicating an active eruption occurred. Venus may still be erupting in places, with basaltic lava oozing out onto the furnace-hot plains. If true, these are the hottest lavas in the solar system in the literal sense, erupting into an air already at 460 degrees Celsius. It's a volcanic nightmare. Eruptions under suffocating skies, hidden from view by clouds, but detectable by orbiters' radar and infrared sensors. Runaway greenhouse and a cautionary tale. Venus likely started much more like Earth, with oceans, temperate conditions, perhaps a gentler climate. But a runaway greenhouse effect, perhaps triggered by escalating solar luminosity or volcanic CO frailness, caused the oceans to evaporate and the climate to catastrophically overheat. Water vapor, a greenhouse gas, and CO frailness accumulated until the planet's heat trapping became irreversible. Today Venus is bone dry, the only water is high in the clouds, and even that is tiny traces. Venus is often seen as a warning of what happens when greenhouse warming goes out of control. In fact, billions of years ago, Venus might have been habitable, only to become a victim of a climatic apocalypse that left it in its present state. It's an arresting thought. Venus is a vision of Earth's possible future if a runaway greenhouse were ever to take hold. Phosphine and the question of life. In 2020, scientists announced the detection of phosphine pH in Venus's cloud decks, a gas associated with life on Earth produced by microbes in oxygen-free environments. The claim was highly controversial, and subsequent analyses questioned the detection, but it highlighted a tantalizing possibility. If any life exists on Venus, it would have to be in the temperate cloud layers, approximately 50-60 kilometers up, where pressure and temperature are Earth-like. Venus's clouds are acidic, but some hardy extremophile microbes on Earth can tolerate very low pH. The phosphine announcement, later disputed, has led to new missions being planned to search for signs of life in Venus's clouds. It remains a wide-open question. Perhaps Venus's story isn't just one of a sterilized hell, but also of a last refuge for life clinging in the skies of an otherwise dead world. Lightning auroras and nightglow. Without a global magnetic field, Venus doesn't have Earth-style auroras at its poles, but it does have a different kind of eerie light show. Venus's entire night-side atmosphere emits a faint infrared glow from oxygen and OH hydroxyl airglow. During Venus's long nights, which last months, the sky isn't completely black. It has a very dim red-orange glow from chemical reactions occurring in the dark upper atmosphere. Also, bursts of lightning in the clouds might create brief local luminous flashes. Astronauts, were they floating in Venus's upper atmosphere, might witness these subtle airglow curtains or distant flashes illuminating the cloud tops. It's as if Venus has a ghostly aurora of its own, not driven by magnetism but by chemistry and storm electricity. Surface of death, Venera's last view. We have only a few photographs from Venus's surface. The Soviet Venera 9, 10, 13 and 14 landers captured haunting panoramas of a dim, barren landscape under an orange sky. The rocks appear pitted and eroded, possibly chemically weathered by the acidic environment. Each lander survived less than 2 hours before the heat and pressure killed it. In Venera 13's final moments, it sent back the only color images, broken, slab-like rocks stretching to the horizon, illuminated by a coppery light. No humans will likely ever directly stand there. It's one of the most inhospitable places imaginable. Those grainy Venera photos remain our only window onto Venus's surface, a silent, airless plain, where even our machines live only for minutes. The silence and deadly conditions are profoundly unsettling, like viewing an alien world that tolerates no intrusion. Mysterious microwave glow. Venus's surface was mapped by radar, but it also emits an unexpected microwave glow. When the first spacecraft and Earth-based radio telescopes studied Venus in radio wavelengths, they found a puzzling bright signal coming from the nightside surface. This turned out to be due to ferroelectric minerals in the Venusian rocks that, when heated, emit strong microwave radiation. Essentially, the hot rocks of Venus act like a microwave oven element, shining at certain radio frequencies. It's a quirk of Venus's mineralogy and heat. One more oddity in a world where normal rules break down. For scientists, it was an eerie surprise. Venus's baking rocks glow at radio energies, broadcasting the story of their extreme heat. It's another reminder that everything on Venus, even the properties of its stones, is pushed to bizarre extremes by the furnace of that planet. The sound of Venus. If you could stand on Venus in an insulated pressure suit with cooling, the sounds around you would be bizarre. The dense CO pies would carry sound extremely well, far distances, and at a different pitch. Your voice, for instance, would vibrate through the heavy air and come out in a deeper timbre than on Earth. A slow drip of sulfuric acid, if any reached the surface, would hiss loudly. Thunder from lightning in the clouds might reverberate for long seconds in the dense atmosphere. Yet, paradoxically, with the constant windless heaviness, there might be an uncanny silence near the ground. No rustling leaves, no running water, just the muffled churn of the thick air and the faint, distant rumble of a storm. It's a speculative but chilling sensory experience, deep, slow acoustics under a crushing sky, in a world where even sound behaves strangely. Mars. The thin, lethal air. Mars's atmosphere is 95% CO4 but extremely tenuous, about 0.6% the pressure of Earth's. This means an unprotected human on Mars would suffocate within minutes, not only from lack of oxygen, but because the low pressure would make blood boil in the lungs and skin. At Mars's surface pressure, approximately 6 millibars, liquid water on your tongue would start to vaporize. In effect, Mars is only a small step above the vacuum of space in terms of human survivability. The immediate threat to an exposed person is not the cold or CO4, but the near vacuum that would cause the bends and embolism gas bubbles in bodily fluids. You'd fizz to death, as one scientist put it. Mars may look invitingly Earth-like with its sunsets and vistas, but its air is a silent killer. Global dust storms of darkness. Mars periodically experiences planet-wide dust storms that shroud the entire planet in darkness for weeks or months. In 2018, one such global storm encircled Mars and hid even the Sun's disk from the surface. NASA's solar-powered Opportunity rover, going on 15 years old, was caught in the storm. The Sun dimmed to nothing, and the rover's batteries drained, plunging it into eternal sleep. When the dust storm subsided, Opportunity never reawakened. These storms, some lasting months, create a deep twilight at noon and drop temperatures drastically. For any future explorers, a global dust storm would be a terrifying challenge, the sky turning butterscotch brown, then black as the dust thickens, sunlight disappearing for weeks, and fine dust infiltrating everything. Mars can go from a sunny day to the equivalent of a volcanic winter planet-wide. The ghost of Opportunity reminds us, a Martian dust storm is not just a spectacle, but a deadly threat that can snuff out our machines, and perhaps people, if unprepared in relentless dusty gloom. Nightmare cold. Though Mars can reach a balmy 20 degrees Celsius, 68 degrees Fahrenheit at midday near the equator, its thin air holds almost no heat. When the sun sets, temperatures plummet precipitously. A pleasant afternoon of -5 degrees Celsius, 23 degrees Fahrenheit might be followed by a midnight of 100 degrees Celsius, 148 degrees Fahrenheit. On average, Mars is colder than Earth's poles. The mean temperature is about -63 degrees Celsius. The coldest measured temperature is around -125 degrees Celsius. Every night on Mars is Antarctic deep winter cold, and without a thick atmosphere, heat radiates away into space in a flash. If you were standing on Mars at sunset, within minutes you'd feel the deadly chill seeping in. By Earth standards, the daily temperature swing on Mars, often over 100 degrees Celsius difference, is otherworldly. Mars's air is so thin that it can't transport heat well, so while you might feel warmth facing the sun, your back might be freezing. It's an environment of thermal extremes that would relentlessly assault an unprotected human, freezing them solid each night. Dried up rivers and ghost lakes. Mars's surface is etched with the telltale scars of flowing water from deep in the past. Gigantic dry river valleys like Mardim Vallis, 700 kilometers long, and delta fans point to a time billions of years ago when rivers ran across Mars and collected in craters to form lakes. Today those rivers are long gone, the channels are empty, and the lakes like Gale Crater, now being explored by the Curiosity rover, are reduced to layered sediment and sulfate salt deposits. The red dust of Mars is largely oxidized iron produced when Mars's water vanished and the surface rusted. These features stand as ghosts of a better past, a time when Mars might have been blue and alive. Now they're bone dry. Imagine walking in one of those great channels. You'd be treading the bed of an ancient river, now just sand and rock under a pink sky. The water that carved it lost to space or locked in permafrost. It's profoundly haunting. Mars is effectively a planetary graveyard of oceans and rivers, a desiccated world that hints at what might have been. Olympus Mels, a volcano the size of Arizona. Mars is home to Olympus Mels, the largest volcano in the solar system, 25 kilometers high, 16 miles, about 3 times Everest's height, and sprawling 600 kilometers across. This shield volcano is so wide that if you stood on its flank, you wouldn't realize you were on a mountain. The slope would appear almost flat, and the curvature of Mars would hide the summit beyond the horizon. Near the top, Olympus Mels has a caldera 85 kilometers wide, a collapse pit that could swallow cities. The volcano is believed to be only tens of millions of years old, possibly even intermittently active in geologic recent history. If you were near its caldera, you'd see cliffs 2 kilometers tall ringing the crater. Climbing Olympus Mels would be an epic and unsettling journey. As you ascend, the air already thin would get even thinner, and you might notice the sky above turning blacker. At the summit you're above much of Mars's scant atmosphere. Olympus Mons is less a mountain and more a small planetic plateau that one could wander unaware. It's a volcano so massive that it challenges our sense of scale, an awe-inspiring relic of Mars's inner fires. Valles Marineris, a colossal canyon, a titanic chasm scars Mars near its equator. Valles Marineris, a canyon system stretching over 4,000 kilometers long, up to 200 kilometers wide, and 7 kilometers deep. It's nearly 10 times longer and 5 times deeper than Earth's Grand Canyon. If it were on Earth, it would span from New York to California in length. Standing at the edge of Valles Marineris, you'd peer into an abyss that reaches 5 times deeper than the Grand Canyon. Terraced walls and landslide debris are visible from orbit. The canyon likely formed from crustal tensions as the nearby Tharsis bulge rose, cracking the planet's surface open. In places, layered sediments and possible chloride salt deposits hint that parts of Valles Marineris might have once hosted lakes or subsurface water. Now it's utterly dry, a gash of stunning proportions. The sheer scale of this canyon, large enough to be seen from Earth through telescopes, is both majestic and intimidating. It's a planetary wound, as if Mars itself bears a 4,000 km scar from some ancient trauma. Marsquakes, and a restless interior. In recent years, Mars has revealed that it is not seismically silent. NASA's InSight lander deployed a seismometer and detected over 1,300 Marsquakes in just 4 years. Most are small magnitude 3-4, but in May 2022, InSight recorded a magnitude 5 quake, the largest ever observed on another planet, which shook the ground for over 6 hours. These quakes suggest that Mars's crust is still settling and cracking, perhaps from cooling and contraction, or from distant meteor impacts. Unlike Earth, Mars has no tectonic plate network to release stress in frequent small quakes, so occasional moderate quakes ripple through its crust. The magnitude 5 monster quake in 2022 released as much energy as the largest nuclear bombs and was near the upper limit scientists expected for Mars. For a future human colony, Marsquakes pose a hazard. The ground trembles on a cold, apparently dead world, reminding us that Mars's interior still has secrets. For example, InSight's data showed Mars's core is molten. There's something eerie about an earthquake on a barren planet, as if Mars itself occasionally groans in its sleep, echoing the tectonic life it once had. Ancient ocean and vanished atmosphere. Geological evidence. Ancient shorelines, delta deposits, and the chemistry of rocks indicates Mars likely had a significant northern ocean long ago. Some models suggest an ocean covering much of Mars's northern lowlands 3-4 billion years ago. Today, that ocean is completely gone. Mars's atmosphere was too thin to keep liquid water stable, and the water either froze underground or was lost to space. Mars's once thicker atmosphere was stripped away by the solar wind after its magnetic field died about 4 billion years past. Mars effectively dried out and suffocated, transforming from a water-bearing world to the arid desert we see now. The MAVEN orbiter has observed solar wind actively eroding the remaining atmosphere, with perhaps 100 grams of gas escaping to space every second. This slow attrition over eons robbed Mars of its lakes and air. In Mars's thin sky today, auroras can occasionally flicker, even without a global magnetic field, caused by solar particles hitting patchy crustal magnetism, a faint echo of a lost magnetosphere. Mars is a mummy of a planet, dried and desiccated by the sun's unfiltered wrath. Mysterious methane whiffs. Mars's atmosphere contains a puzzling trace gas, methane, which on Earth is largely produced by life or geochemistry. Rover and orbiter measurements have caught methane at a few parts per billion, with strange seasonal patterns and sudden spikes up to 10x background levels. Methane should break down in a few centuries under solar radiation, so whatever is producing it on Mars is likely active today. Scientists debate whether it's due to subsurface microbial life, extremely speculative, or chemical reactions like water reacting with certain rocks, serpentinization, or slow release from methane clathrate ices. Curiosity observed that methane peaks at night and varies with the seasons, and once saw a spike about 40 times above normal. Meanwhile, Europe's trace gas orbiter high above has seen virtually no methane globally, deepening the mystery. It's as if methane belches from the Martian ground in localized bursts and then gets trapped near the surface or destroyed. Mars teasing us with a possible signature of life or peculiar chemistry is both exciting and unsettling. It's a detective story still unfolding. Those tiny puffs of methane could be the last exhalations of a warm, wet Mars, or even biosignatures from deep underground. We simply don't know yet. The Mars Curse, Fallen Robots. Mars has been the graveyard of many missions. Before the recent string of successes, roughly half of all Mars missions failed, crashing, missing the planet, or otherwise dying. This led to a folklore of a Mars curse. Even today, the Martian surface is littered with the wreckage of human ambition, the silent husk of the Schiaparelli lander, which slammed into Mars in 2016, the lost Beagle 2, which reached the surface in 2003, but its solar panels failed to deploy, Soviet landers Mars 2 and Mars 3, 1971, which died in dust storms, and more. Of the successes, several rovers now sit defunct, Spirit stuck in sand in 2010, Opportunity killed by the 2018 storm, and others. When the winds are quiet, Mars's deserts are eerily silent, but not empty. They hold the remains of our machines, like bones on a desert floor. Future explorers might stumble upon an old Pathfinder or Viking lander, coated in dust, a monument to past exploration. Mars takes a toll. It's where we repeatedly reach, and often fall short, leaving behind a somber trail of technological ghosts. Phobos, doomed moon. Mars's inner moon Phobos orbits extremely close, 6,000 kilometers above the surface, and is spiraling inward a few centimeters per year. Phobos' fate is sealed in about 50 million years. It will either crash into Mars or be torn apart into a ring. If it breaks up, Mars could temporarily gain a set of rings like a mini Saturn. For now, Phobos causes eerie eclipses on Mars, solar eclipses that are not total, but speedy annular eclipses, where Phobos crosses the sun's face as a large dark disk. Rover cameras have captured these events, a small moon racing across the sun, surrounded by a glare. It reminds us that Mars's moons are not forever. Phobos, a lumpy asteroid-like object, 22 kilometers across, will eventually either smash into Mars, blasting a crater, or rip into pieces, forming a ring arc. Mars's sky will then be encircled by the debris of its former moon. For now, Phobos' impending demise also produces a menacing effect on Mars. It raises tidal stresses that may contribute to Marsquakes and slowly drag on Mars's rotation. It's a cosmic clock, counting down in Mars's sky. 7 minutes of terror. The descent. Though this is more about our experience than Mars itself, it's an undeniably anxiety-inducing aspect of Mars. Landing on Mars is so harrowing that engineers call the entry, descent, and landing sequence the 7 minutes of terror. A spacecraft must endure atmospheric entry at 21,000 kilometers per h, temperatures of 1,500 degrees Celsius, supersonic parachute deployment, and then often a rocket-powered or sky crane final maneuver, all autonomously, with no real-time help from Earth. Mars's thin air is just thick enough to cause extreme heating, but too thin to slow a craft sufficiently by parachute alone. Many missions have failed at this stage. The Curiosity and Perseverance rovers recorded their landings. If you watch the footage blended with animation, you see the chaotic buffeting, dust blasting, and then sudden stillness as the rover finds itself sitting on an alien world. For 7 minutes, a robotic explorer is literally on the edge of destruction. Success means new life on Mars's surface. Failure means joining the wreckage already there. No matter how routine we make it, those moments encapsulate the silent hostility of Mars. It does not welcome visitors easily. Radiation, invisible killer. Mars lacks a global magnetic field and has a very thin atmosphere, so the surface is bathed in high-energy cosmic rays and solar radiation. A human on Mars would receive about 50 times more radiation per year than on Earth's surface, enough to significantly raise cancer risk and cause acute radiation sickness during solar storms. This radiation environment is so intense that it directly alters Martian soil. It destroys complex organic molecules in the top layers, complicating the search for life's building blocks by rovers. They must dig or drill to find preserved organics. During the 6-month cruise to Mars and operations on the ground, rovers like Curiosity have dosed out more cumulative radiation than some nuclear workers receive in a lifetime. For future astronauts, living on Mars will require habitats buried under meters of regolith or water shielding to be safe. Mars is a silent radiation field, with charged particles zipping through the air and ground. You won't see or feel them, but they'll be there, an ever-present hazard, the ghost of a vanished magnetosphere. Tantalizing traces of ancient life. Mars today is sterile on the surface, but it wasn't always so. NASA's Perseverance rover is exploring an ancient river delta in Jezero crater, precisely because such environments on Earth teem with life and preserve microfossils. Mars rovers have found organic molecules like thiophenes and aromatic hydrocarbons in 3.5 billion-year-old mudstones. Curiosity also observed fluctuating levels of atmospheric methane, possibly seasonal. While no conclusive biosignatures have been found, the hints are intriguing and unsettling. If Mars ever had life, it might still lurk underground in brines, or its remnants might be hidden as microscopic fossils in crater lake sediments. Imagine discovering that life twice arose in our solar system, a profound revelation that Mars may yet hold. Alternatively, imagine we find nothing, implying a once habitable Mars never sparked life, a sobering counterpoint to Earth. Either answer, life on Mars or lifelessness despite habitability, carries an existential chill. Mars guards this secret in its rocks, and we have only begun to crack them open. Jupiter. The King's deadly halo. Jupiter is surrounded by the most intense radiation belts in the solar system. Its magnetic field traps charged particles, electrons, protons, ions in colossal bands, a 200,000 Kelvin increase in radiation flux compared to Earth's Van Allen belts. The dosage near Jupiter can instantly disable unshielded electronics and would be fatal to humans in minutes. For example, at Jupiter's orbit, NASA's Juno spacecraft must take a special polar trajectory, diving in and out over the poles to avoid the brunt of the radiation, and its sensitive components are inside a titanium vault. The Moon Io, orbiting within these belts, is constantly blasted. Its surface is thought to be plasma sputtered by the particle flux. Any astronaut venturing near Io or the belts would receive a radiation dose thousands of times the lethal limit. It's effectively an invisible halo of death around Jupiter, generated by the planet's titanic magnetic field. Even far-out moons like Europa sit just outside the worst of these belts, but still inside a hazardous zone. It's as if Jupiter wears an invisible crown of energetic fury. Beautiful auroras are the visible byproduct, but the unseen radiation would annihilate earthly life. Any future spacecraft that tours Jupiter must navigate this minefield of high-energy particles, or risk joining the list of fried electronics that dared to trespass too long in Jupiter's domain. The Great Red Storm. Jupiter's Great Red Spot is a mammoth storm wider than Earth that has raged for at least 350 years since telescopes first observed it. But this ancient cyclone, a vast anticyclone, is shrinking and fading in our time. In the late 1800s, it was estimated at 40,000 kilometers across. Today it's about 15,000 kilometers across, less than half the size it used to be. In recent decades, the spot's waistline has been contracting by hundreds of kilometers per year, and its once brick red color has sometimes paled to salmon, or even yellow. No one is sure why. Perhaps changes in Jupiter's climate or jet streams are strangling it. If the trend continues, the Great Red Spot could become a Great Red Memory within a few decades or centuries. It may even break apart into smaller vortices, as some smaller spots on Jupiter have. For now, though, it is still a towering, 3D vortex, with winds of approximately 430 km/h, and its crimson clouds rich in complex organic molecules or sulfur compounds reach high above Jupiter's other cloud decks. It's essentially a gargantuan hurricane that could swallow our whole planet. The idea that this behemoth, stable since the time of Galileo or earlier, might die within our lifetimes is strangely melancholy. The Great Red Spot's possible demise is a reminder that even on Jupiter, nothing lasts forever, not even a centuries-old storm the size of Earth. Lightning and sprite specters. Jupiter hosts storm phenomena far beyond Earth's. Its thunderstorms, deep in its water cloud layer, are ferocious. Flashes detected by Voyager and Cassini show lightning bolts up to 100 times more energetic than Earth's strongest lightning. In the thin gas above these storms, Juno has spotted mysterious ultraviolet flashes called transient luminous events, essentially sprites and elves, types of high-altitude lightning dancing in Jupiter's upper atmosphere. These brief, ghostly flashes, seen as narrow UV streaks, are analogous to the sprites seen above earthly thunderstorms, but it's the first time we've caught them on another world. They likely appear as expanding rings or tendrils of glowing plasma high above Jupiter's clouds. For an observer in Jupiter's skies, these would be bizarre, silent fireworks lighting up the thin air at the edge of space. The presence of alien lightning and exotic electrical phenomena in Jupiter's atmosphere paints a picture of a dynamic, violent world. One can imagine looking down upon Jupiter's cloud tops during a storm, beneath the anvil of a great thunderhead. Huge lightning bolts crackle. Above it, a fleeting sprite flares into being, a red jellyfish-shaped glow, and fades in milliseconds. Jupiter's storms are not just bigger than Earth's, they're producing light shows literally out of this world. Liquid metal and helium rain. Deep inside Jupiter, at pressures of 1–2 million atmospheres and temperatures around 5,000–10,000 degrees Celsius, normal physics gives way to the bizarre. Hydrogen, normally a gas, is compressed into a liquid metallic form, an electrically conducting fluid that powers Jupiter's mighty magnetic field. In a shell above Jupiter's core, temperatures and pressures cause helium to condense out of the hydrogen and form droplets, literally helium rain falling deeper into the planet. This rain of helium releases heat as it descends, which is thought to be one source of Jupiter's internal energy, and explains why Jupiter's upper atmosphere is depleted in helium. It's raining out. In essence, Jupiter has weather even inside a cycle of helium precipitation analogous to rain. It's a mind-bending concept, rains of liquid neon helium mix, falling through a metallic hydrogen sea. The Galileo entry probe sampled Jupiter's air in 1995, and indeed found less helium than expected. Supporting this model, Galileo itself was destroyed by the crushing pressure around 22 bars, after 57 minutes of descent. So in Jupiter's hidden layers, as alien as any realm in the universe, there might be a continuous shower of liquid helium raindrops the size of cherries, falling for thousands of kilometers. It's a realm as far removed from human experience as one can imagine. Biggest magnetosphere in the solar system. Jupiter's magnetic field is 20,000 times stronger than Earth's, and it carves out a magnetosphere that envelops not just Jupiter but its whole moon system. This magnetosphere, the region dominated by Jupiter's magnetic field, stretches at least 3 million kilometers sunward, and on the night side it extends in a sprawling tail that sometimes reaches Saturn's orbit. If we could see Jupiter's magnetosphere glowing, it'd appear several times larger than the full moon in our sky. Charged particles funneling along Jupiter's field produce constant intense auroras at its poles, ovals of shimmering UV and infrared light that never turn off. These Jovian auroras can be 100 times more energetic than Earth's auroras and are fed not only by the solar wind but also by volcanic material from Io. The spectacle is permanent, a continuous polar lightning glow. Yet, despite the strength of the field, standing near Jupiter you wouldn't feel anything, except perhaps the disorientation of your compass wildly pointing away from Jupiter's poles, a hypothetical, since you couldn't stand in Jupiter's atmosphere. Jupiter's magnetosphere is a silent giant wielding immense influence. It even induces auroras and electrical currents on Io. Io's flux tube carries a 5 million ampere electric current between the Moon and Jupiter, sparking Io's own auroral footprint on Jupiter. No other planet's magnetic domain comes close. Jupiter is a miniature pulsar in some respects. If Earth had Jupiter's magnetosphere, it would engulf the Moon. Within this bubble, everything, radiation, plasma, electric currents, is pushed to extremes. Falling into Jupiter, the bottomless abyss. Jupiter has no solid surface, so a probe or person descending into it would never hit ground. They would be crushed and melted by increasing pressure. In 1995, the Galileo probe plunged into Jupiter and broadcast data for 58 minutes before the pressure, 23 atmospheres, and heat, approximately 153 degrees C, crushed it. It was about 150 kilometers below the cloud tops at that point. Had it somehow survived longer, it would have encountered pressures of thousands of atmospheres and temperatures of thousands of degrees as it went deeper. Any object falling into Jupiter is ultimately absorbed into its fluid interior. In a sense, Jupiter could be viewed as a very small star, an immense ball of fluid where sky and sea blur into one. The lack of a surface means Jupiter's oceans of hydrogen just get denser with depth. If you tried to parachute into Jupiter, you'd descend through tan and white cloud decks, ammonia ice, the last things you'd see, then deeper into gloom, the air pressure mounting. Eventually, long before seeing any exotic metallic hydrogen, you'd be crushed like a tin can, and your remains would sink and dissolve in Jupiter's hot depths. It's a one-way trip into oblivion. Auroras like no other. Jupiter's polar auroras are permanent and incredibly powerful, hundreds of times brighter than Earth's. Hubble and Juno have observed them in UV and infrared, vast ovals lighting up the Jovian poles. Unlike Earth's occasional auroral substorms, Jupiter's are continuously driven by Io's plasma and rapid rotation. At Jupiter's poles, you'd see an almost constant curtain of faint purplish-blue light rippling around the pole, though Jupiter's thick atmosphere beneath might obscure the view from within. These auroras put out as much energy as 10,000 nuclear reactors. Jupiter's auroral power is on the order of 10 circumflex 13 watts. Juno discovered dawn storms, intensifications of auroras in the pre-dawn sector, where brightness surges tenfold. Strangely, Jupiter's auroras defy some expectations. They don't vary with solar activity as much as Earth's, and can be anti-correlated between hemispheres. They are essentially a glowing brand on the planet from its enormous magnetospheric engine. To witness them up close would be uncanny. A giant planet's polar atmosphere glowing continually, spiked by flashes and waves as magnetic storms pass. It's a light show powered not just by the Sun, but by Jupiter's own rotation and Io's volcanic sacrifice to the magnetosphere. Nearly a star, Jupiter is often called a failed star. In terms of composition, it's basically solar, mostly hydrogen and helium. If it had grown to about 80 times its current mass, Jupiter's core pressure would have ignited hydrogen fusion, and it would have become a small red dwarf star. Of course, adding that much mass was not possible in our Sun's protoplanetary disk, so instead Jupiter settled as the most massive planet. Still, Jupiter emits a faint internal glow. It radiates about 1.6 times the energy it gets from the Sun, leftover heat from its formation, and possibly helium rain. In infrared, Jupiter actually shines, and if you were far out in the solar system, you could detect Jupiter as a dim, warm object. In a sense, Jupiter is like a star embryo that didn't quite make it. Sometimes in sci-fi, people imagine igniting Jupiter to create a second sun, as in Arthur C. Clarke's 2010. In reality, that's not feasible without adding enormous mass, but the comparison is apt. Jupiter holds 75% of all planetary mass in the solar system, more than twice the mass of all other planets combined, and its gravity dominates the architecture of the outer solar system. It even has a miniature solar system of moons. If you look at Jupiter and imagine it 80 times heavier, suddenly the night sky would have two suns. It's a reminder of how fine the line can be between planet and star, and how in a different cosmic roll of the dice, our solar system might have been a binary star system with little room for us. Diamond rain. Deep in Jupiter's atmosphere, conditions may be right for diamond precipitation. Lightning storms in the upper cloud layers can convert methane into soot, carbon. As that carbon falls deeper, pressure and temperature ramp up, compressing the carbon into diamond crystals in the 1,000–6,000 kilometers depth range. Jupiter's interior might have diamond hailstones forming and raining down, possibly melting into liquid carbon, deeper still. While this sounds like science fiction, laboratory experiments and equations of state for carbon at high pressure support the plausibility. If true, Jupiter and Saturn could be cosmic diamond mines, with uncountable tons of gem-quality diamonds forming in their skies. Of course, retrieving them is another matter. They presumably sink toward the core and perhaps dissolve in the fluid metallic hydrogen. But it's a striking thought on Jupiter. Not only do helium and ammonia rain, but perhaps literal diamonds fall from the sky in the deep dark layers. The riches of Jupiter are ultimately inaccessible and transient, ephemeral jewels that condense from soot and sink into darkness. Volcanic electric guitar, Io's flux tube. Jupiter's moon Io is the most volcanically active body in the solar system, thanks to Jupiter's tidal flexing. Io's volcanoes constantly erupt sulfur and So-D gas. These materials become ionized in Io's orbit, forming a torus of plasma around Jupiter. Jupiter's fast rotation drags this plasma, and along with Io's motion, sets up a giant electric current, about 5 million amperes, flowing along magnetic field lines between Io and Jupiter's poles. This Io flux tube generates a glowing footprint aurora on Jupiter, where it enters the atmosphere, and likely auroras on Io as well. Essentially, Io is hooked to Jupiter by an electromagnetic umbilical cord. It's a phenomenon unlike anything on Earth, a moon causing bright auroral spots on its parent planet. If you were on Jupiter's cloud tops under the flux tube, you might see a glowing patch that waxes and wanes as Io swings around. Meanwhile, Io's surface itself is charged and connected, a huge electrical circuit linking two worlds. The concept is spooky. Stand on Io's night side, and you'd be bathed in Jupiter's auroral glow, connected by invisible magnetic lines carrying megaamps of current. Jupiter essentially plays Io's flux tube like a giant electric guitar, accelerating particles and generating powerful radio emissions detectable from Earth. It's a reminder that Jupiter's reach isn't just gravitational, it's electromagnetic, ensnaring its moons in an energetic embrace. Cometary impacts. Scars on a giant. In July 1994, humanity witnessed a cosmic collision in real time. Comet Shoemaker, Levy 9, had broken into fragments and slammed into Jupiter one by one. The impacts created enormous dark scars in Jupiter's atmosphere, some larger than Earth, that persisted for months. The explosions were tremendous. One fragment, G, released energy equivalent to 6 million megatons of TNT, far beyond Earth's entire nuclear arsenal. Plumes shot thousands of kilometers high into space before raining back down. For days, amateur astronomers could see the black splotches on Jupiter through backyard telescopes. It was a stark demonstration that Jupiter, with its powerful gravity, serves as a gravitational vacuum cleaner, or enforcer, intercepting comets that might otherwise wander into the inner solar system. The ghostly bruise marks on Jupiter gradually dissipated as winds mixed them, but for a time, Jupiter wore the black eyes of that impact. If such an impact happened on Earth, well, Earth would be sterilized. Jupiter took it in stride, essentially shrugging off impacts of catastrophic magnitude and healing within weeks. There's something chillingly comforting about Jupiter's role. It likely spares the inner planets from some cometary doom, but it also reminds us that celestial impacts are not rare on geological timescales. Jupiter bears the scars of impacts so colossal our minds strain to comprehend them. Shoemaker, Levy 9 was a preview of the kind of extinction-level events Jupiter can absorb. In a sense, Jupiter might be the reason Earth hasn't had as many life-erasing strikes. The king of planets sometimes sacrificially takes the hit. Flattened by speed, Jupiter rotates extremely fast. One day is just 9 hours 56 minutes. This rapid spin causes Jupiter to bulge at the equator. In fact, Jupiter is noticeably ablate. Its equatorial diameter, approximately 142,984 km, is about 7% larger than its polar diameter, approximately 133,708 km. The planet is visibly fatter around the middle. This means gravity and weight differ from pole to equator. An object at Jupiter's equator is flung outward slightly by centrifugal force. If you could stand on a hypothetical solid surface at Jupiter's poles versus equator, you'd weigh a bit less at the equator due to the spin. The rapid rotation also drives Jupiter's banded cloud structure, the east-west jet streams that create its dark belts and bright zones. Those bands are essentially fluid rings spinning around at differing speeds and directions, and the Coriolis effect from the fast spin makes storms stretch into elongated shapes. The Great Red Spot itself is likely limited in latitude by the powerful jets above and below it. Jupiter's tremendous rotation speed hints at how it formed, gobbling up gas from the young sun's disk and spinning up like a skater pulling in arms. It's spinning so fast that if it were just 10% faster, it might start breaking apart, exceeding the centripetal limit for its composition. Thus, Jupiter is near the edge of rotational stability, a whirling behemoth just held together by gravity. A fuzzy, diluted core, Juno mission data, revealed that Jupiter's core is not the compact nugget scientists expected. Instead, Jupiter seems to have a fuzzy core, a diffuse region of heavy elements extending perhaps halfway out from the center. One hypothesis is that long ago during Jupiter's formation, an embryonic protoplanet of 10-20 Earth masses crashed into young Jupiter, shattering its solid core and mixing heavy elements upward. The result today, Jupiter's inner 30–50% radius, is a dilute core of slurry-like enrichment without a sharp boundary. This giant impact theory would also explain why Jupiter's atmosphere contains heavier elements in greater proportion than the Sun, the impactor-delivered metals. If true, Jupiter carries the remains of an entire infant planet inside it, absorbed eons ago. It's haunting to consider. Jupiter may have once had a stable solid core, but a violent collision turned its interior into a stirred soup. In the long run, the heavy elements will resettle somewhat, but Jupiter's heart will remain fuzzy for billions of years. We effectively found that Jupiter's gargantuan body bears a cosmic scar deep within, a smeared memory of an ancient impact that we can deduce only through gravity measurements and modeling. The largest planet has the largest secrets, and one of them is that its core is a blur, not a crystal. Alien auroral sounds. Jupiter's auroras not only glow, they also emit powerful radio waves that we can convert to audio. The emissions, known as auroral colorimetric radiation, have been recorded by spacecraft like Galileo and Juno. When sped up and translated to sound, they are unearthly whooshes and whistles and static bursts, like the roar of a cosmic ocean or an alien whale song. These radio emissions are caused by electrons accelerated in Jupiter's magnetosphere slamming into its atmosphere. On Earth, very low-frequency radio waves from auroras called spherics or auroral chorus can sometimes be heard via radio receivers as chirps and whistles. Jupiter's are far more intense. Listening to Jupiter's radio storms is an eerie experience, a haunting howl and crackle that reminds us these auroras are electromagnetic phenomena on a titanic scale. Juno detected one such emission right as it spotted a sprite, possibly the radio crackle from the sprite itself. If one had radio ears on Jupiter, the polar regions might be filled with these sounds, oscillating as magnetic field lines oscillate. On the night side, Jovian auroras likely produce auroral hiss that could be picked up by a suitably tuned receiver. It's as if Jupiter sings, not in audible light, but in radio, broadcasting the tale of its energetic particles to anyone who cares to tune in. In those ghostly radio songs of Jupiter, we hear the solar wind, Io's volcanoes, and Jupiter's spinning magnet all interacting in a cosmic symphony. A mini solar system. Jupiter has 95 known moons and counting, effectively a miniature solar system of worlds, each with its own character. 4 are planet-sized volcanic Io, icy Europa, with a possible subsurface ocean, huge Ganymede, larger than Mercury, with its own magnetic field, and battered Callisto. These moons influence each other and the planet in complex ways. Io feeds Jupiter's magnetosphere with plasma. Europa likely has a deep saltwater ocean under its ice that might harbor life. Ganymede's magnetic field creates auroras in its thin atmosphere. From Jupiter, these moons would be spectacular in the sky. Ganymede would appear the size of a golf ball held at arm's length, constantly changing phase and position. Eclipses and transits are frequent. You'd often see the shadows of moons as black spots racing across Jupiter's cloud tops. At least once or twice per day, Jupiter Day, a moon might eclipse the sun for a few minutes, casting a moving oval shadow. There's a quiet eeriness to Jupiter's system. Nights on the moons can be lit by Jupiter's bright disk, providing reflected Jupiter shine, and sometimes multiple moons line up in the sky like a cosmic mobile. It's beautiful, but also, for any hypothetical future human settlers on these moons, a reminder of Jupiter's dominance. It's a colossal parent planet, looming overhead, tugging ceaselessly at its children. The moons are tiny worlds enmeshed in Jupiter's magnetospheric web, sometimes trading particles and glow, Io's and Europa's footprints, Ganymede's auroral bands. To stand on any of these moons is to feel that you are in the realm of a gas giant, a landscape dominated not by your own world, but by the enormous striped planet hanging in the sky, filling the heavens. No other place in our solar system so vividly demonstrates planetary power. Saturn. The hexagon storm, crowning Saturn's north pole, is a striking and bizarre structure, a hexagon-shaped jet stream in the clouds, each side about 14,500 kilometers long, dwarfing Earth's diameter. Discovered by Voyager and observed in detail by Cassini, this six-sided vortex rotates with Saturn's rotation period and contains a roaring hurricane at its center. The hexagon's origin is still not fully understood. Lab experiments can recreate polygonal flow patterns, so it likely arises from a standing wave in Saturn's atmosphere. But seeing a nearly perfect hexagon locked onto a planet's pole is deeply eerie. It's a cloud pattern, geometric and seemingly unnatural, yet there it is. The hexagon has persisted for at least 40 years, probably much longer, with only subtle color changes. At the pole's very center lies a hurricane-like eye approximately 2,000 km across, with a colossal eye-wall clouds towering 50 kilometers high. Winds around the hexagon flow approximately 320 km/h. It's as if Saturn wears a vast pale blue stop sign at its pole. If one could hover above Saturn's north pole, you'd see this immense hexagonal band circling below, perhaps with the central vortex peering up like a dark pupil in a strangely geometric eye. It's nature's reminder that fluid dynamics can produce shapes that look almost artificial. The effect is frankly unsettling. Among the soft wavy bands of Saturn's atmosphere sits a huge angular shape, a cosmic mystery in motion. Rings in peril. Saturn's magnificent rings, spanning over 270,000 kilometers in diameter, but only approximately 10 meters thick in places, are not permanent adornments. Recent research confirms Saturn is losing its rings at a worst-case rate of 10,000 kilograms per second, in the form of a dusty ring rain falling into the planet's equator. This ring rain is charged water ice, and organics pulled by Saturn's gravity and guided by its magnetic field into the upper atmosphere. Cassini's final orbits measured that material and found it to be a downpour, not a drizzle. At that rate, Saturn's rings, which may be at most approximately 100 million years old, could disappear within 100–300 million years. In cosmic terms, they're ephemeral. There was a time when Saturn likely had no large rings, and perhaps will again. For us it's sobering. We live in a unique epoch when Saturn's rings are broad and bright. Future observers in the far future might see a mostly bare Saturn, or just a vestigial ring system like Jupiter's. Saturn's rings are essentially a funeral pyre, a disintegrating moon or captured comet, shredded within the Roche limit, now being ground to icy dust and spiraling into Saturn. Watching Saturn's rings is to witness something enormous yet transient. Every second, countless ring particles succumb to drag and gravity, leaving their cosmic dance to plunge like icy rain into Saturn. Someday, perhaps, Saturn will wear only a subtle ring, and aliens studying ancient records might wonder at the glorious hoops it once flaunted. We are lucky to behold them now. They are arguably the most beautiful visible structure in the solar system, and they are on borrowed time. Spokes in the rings. Saturn's rings are normally elegantly concentric, but sometimes mysterious dark spokes appear on the rings, radial features that rotate along with the rings like ghostly fingers. First seen by Voyager, these spokes are short-lived clumps of tiny charged dust levitated above the ring plane by Saturn's magnetic field. They tend to appear around Saturn's equinox when the sun's angle on the rings is low. These spokes can be as large as Earth in length, yet appear and vanish over hours or days. They confused scientists. How could rings, essentially trillions of orbiting particles, show features seemingly defying Keplerian motion? We now think it's essentially an electrostatic effect. As Saturn's magnetosphere changes, small ring particles get charged and momentarily lifted, creating a shadow or discoloration that co-rotates with Saturn's rotation, not the ring's orbital speed. To an observer near the rings, these spokes would likely be invisible, except by the dimming they cause. But imagine Saturn's rings edge on with the sun behind. You might see darker radial bands appear as if some enormous presence dragged a broom across the rings. It's an almost supernatural phenomenon, shadows that shouldn't be, spokes in a wheel that is otherwise pure physics. The fact that these spokes come and go with seasons. They disappeared in the 1990s and returned as Saturn approached equinox in 2009 and onward adds to their mystique. They are a seasonal weather pattern in the rings, ring weather. All told, Saturn's rings are not static jewels. They have their own flickering, transient features that remind us even something as seemingly perfect as the rings holds surprises. Helium rain and extra heat. Like Jupiter, Saturn emits more energy than it gains from sunlight, about 2.3 times as much. This puzzled scientists because Saturn is smaller than Jupiter and should have lost more of its primordial heat by now. The leading explanation is helium rain. As Saturn's interior cools, helium becomes immiscible in hydrogen and forms droplets that fall toward the core, releasing gravitational energy as heat. In effect, Saturn has helium drizzles deep within, which keeps it warmer than otherwise for its age. This process also depletes helium from the upper layers. Matching what Voyager observed, Saturn's atmosphere has less helium than Jupiter's. It's an uncanny concept that rains we will never see govern the thermal evolution of an entire planet. If you were at Saturn's cloud tops, you'd find them about 20K warmer than they would be without internal heating. Saturn's glow in infrared is the signature of countless helium droplets falling in an alien rain, tens of thousands of kilometers below. The existence of this invisible rain was inferred only by careful science, but it's likely raging even now in Saturn's depths. Saturn's entire visage, the tranquil golden bands, the majestic rings, is underpinned by this hidden heating. It's a bit like a fever from within. Saturn glows with ghost heat left from formation, sustained by a gentle helium drizzle inside. Storms that engulf a planet. Approximately every 20-30 Earth years, Saturn erupts with a great white spot, a planetary-scale megastorm. These are massive thunderstorm systems that can grow to encircle the entire planet in whitish clouds. One last occurred in December 2010, earlier than expected, and it churned through much of 2011. Cassini observed it in detail. A 10,000 km wide brilliant stormhead spawning a band of turbulent clouds that wrapped around Saturn's northern hemisphere. Lightning rates were astonishing, up to 10 flashes per second at peak, far higher than terrestrial superstorms. The storm generated as much energy as the Earth receives from the Sun in a year. Eventually, this great white spot split, and its own tail overtook it. The head ran into the backside of the storm's tail, after encircling the globe, effectively strangling the storm, an extraordinary dynamic where a storm chokes on its own wake. These megastorms leave lasting effects. Cassini saw that the 2010 storm disrupted Saturn's tropopause and produced new haze. The spot from 1933 left a subtle increase in ammonia detected decades later. Imagine witnessing a great white spot from Saturn's cloud tops. You'd see a line of towering thunderheads stretching to the horizon, unleashing monster bolts, and probably intense precipitation of ammonia-rich mushballs, slushy hail. The sky would light up repeatedly in a strobe of lightning. Over weeks that storm would spread and wrap around the planet until the entire band around you is a chaos of white cloud, howling winds and incessant thunder. It would be the storm to end all storms, consuming itself in a grand act of Saturnian weather. Only 5 such storms have been observed since 1870, making them once-in-a-lifetime events. If one happened today, it would be easily visible in backyard telescopes as a white scar on Saturn's honey-colored disk. A planet-wide thunderstorm every few decades, yet another facet of Saturn's split personality, outwardly serene for years, then suddenly a global maelstrom. An eye at the pole. Saturn's south pole hosts a colossal hurricane-like vortex as well, first seen by Cassini in 2006. This polar cyclone has a nearly circular eye approximately 8,000 km across 2/3 Earth's diameter, with a well-defined eye wall of clouds towering 75 kilometers high. It looks strikingly like a terrestrial hurricane, but one locked over the pole and not driven by warm ocean, since there is none. It may be fueled by small amounts of atmospheric moisture and the heat of descending air, or perhaps by energy from Saturn's interior. The winds around the eye blow approximately 550 km/h, and inside the eye, it's relatively calm and clear to deeper layers. Unlike Earth hurricanes, this vortex doesn't drift, it's pinned on the pole, and it has persisted for at least the 15 years Cassini watched. It's as if Saturn's pole has a permanent giant cyclone drilled into it. The visuals are stunning. False color images show the eye as a deep red rose, with a green-hued eye wall in infrared mapping, an alien storm akin to a stylized flower. For an observer floating above Saturn's pole, it would be an awe-inspiring sight, a massive circular storm hole in the planet, very different from the hexagon on the North Pole. The existence of this polar cyclone also hints that Saturn's poles trap bizarre weather, a hexagon in the north, a huge hurricane in the south. These features have likely swirled for decades or more. They are essentially permanent cyclones. On Earth, even the most long-lived hurricane dissipates after a few weeks when it hits land or cold water. On Saturn, a polar hurricane can last indefinitely because it's powered by the planet's overall heat and rotation. It's like an immortal storm, a literal eye of Saturn gazing upward. Low density and slow fall. Saturn is so low density, average 0.687 g per cc, it would float in water if you had an ocean big enough that gravity at its cloud tops is actually only about 1.065 times Earth's. Yet, if you tried to parachute into Saturn's atmosphere, you might never reach a solid surface, but you could descend for hours through layers of cloud and haze. The experience would be otherworldly. Initially, you'd fall through pale yellow ammonia clouds in the upper atmosphere. Deeper down, approximately 100 km, the pressure would build and you'd encounter ammonium hydrosulfide clouds, brownish clouds, and then perhaps water ice clouds further below. Though at those depths, approximately 200 km down, approximately 20 bar, the temperature is tilde 0 degrees C, and it's dark. Sunlight has been mostly absorbed above. The atmospheric density would become soup thick. You'd likely be crushed or heated to death by approximately 130–150 kilometers below the clouds, pressure approximately 27 bar, temp tilde 150 degrees C. Long before hitting any core, you or your probe would be a flattened, overheated pancake of metal and flesh. Saturn, like Jupiter, allows no visits to its surface because it has none. only an endless gradient into oblivion. But interestingly, because Saturn's gravity is lower, terminal velocity for a falling object might be lower. One could theoretically deploy a balloon and float in Saturn's upper atmosphere. Some scientists have proposed robotic balloons. The thought of drifting in Saturn's upper skies, with the rings possibly visible as a thin line if near the terminator, and perhaps lightning flickering below, is eerily beautiful. But it remains theoretical. Saturn's low density belies an important truth. Under the pretty exterior, it's mostly a gigantic ball of compressed hydrogen and helium. Its lightweight bulk that is deadly in embrace, a gossamer planet from afar that turns into a crushing ocean of gas up close. Enceladus's gift, a second ring. Saturn's small moon Enceladus has geysers that shoot water vapor and ice grains out through its south polar cracks. These plumes feed an entire ring of Saturn, the E-ring, a broad diffuse ring outside the main ones. So here's a spooky relationship. A moon with a subsurface ocean is actively coating Saturn with its ocean spray. Some of that water falls into Saturn. Cassini detected water from Enceladus raining into Saturn's atmosphere at high latitudes, affecting ionospheric chemistry. So Saturn is being literally sprinkled by a moon's hidden sea. If microbial life exists in Enceladus's ocean, traces of it might be riding those geyser particles and becoming part of Saturn's rings, or falling into Saturn itself. It's a wild concept, life's ingredients from a moon ending up in the planet's atmosphere. Cassini actually flew through Enceladus's plume and detected complex organics. Enceladus's plume is like a cosmic fountain of youth for Saturn's rings, sustaining the E-ring as others wane. Eventually Enceladus may exhaust or chill, and the plume will cease, and then the E-ring will dissipate. Saturn's rings, again, are ephemeral, partly because the sources like Enceladus won't always be active. There's a profound cycle here. Saturn's gravity and tidal forces keep Enceladus hot and active. Enceladus repays Saturn by painting it with water and ice, giving it a ring, and perhaps helping nurture the habitability of other moons by distributing materials. It's a symbiosis, but also a bit of a sacrifice. Enceladus is bleeding mass to Saturn, about 200 kilograms of water per second through the plume. Billions of years hence, Enceladus might freeze out, having lost a not insignificant portion of its mass to space and Saturn. In the delicate filigree of Saturn's rings and moons, Enceladus's ghost will live on as particles of ice orbiting Saturn, long after its geologic heartbeat stops. The sound of Saturn's rings. When Cassini plunged between Saturn and its innermost ring during its grand finale orbits, it carried a plasma wave instrument that recorded electromagnetic oscillations, essentially sounds of the ring particles and space environment. These recordings, when converted to audio, turned out to be surprisingly eerie. One moment, passing just inside the rings, Cassini found utter silence, fewer particles than expected, a lucky gap. But crossing ring plane regions with more dust produced bursts of crackling and popping, like hail on a tin roof. That was microscopic ring particles striking the spacecraft at high speed. It was the sound of ring rain, the whispers of dust that pervade Saturn's environment. Saturn's rings themselves can oscillate like a drumhead. Disturbances cause waves in the rings that can even be sensed in stellar occultation data. If we convert those waves to sound, you essentially hear the rings ringing, a resonate hum at certain frequencies. And Saturn's rotation modulates the rings too, in subtle gravitational interactions that are again almost musical. In fact, one can describe ring wave patterns with Fourier harmonics. In essence, Saturn's whole system has a music of the spheres. The rings hum with gravity waves, the planet sings with radio emissions, the plasma disk buzzes with charged particles. It's a very subtle symphony. But Cassini let us eavesdrop. It stands to reason that an intrepid and hypothetical future explorer could listen to Saturn's environment on a radio receiver and hear the pops of ring particles, the hiss of Saturn's ionosphere, and the rising tone as they enter a denser region. It's an environment that feels placid when seen, silent vacuum and graceful rings, but it definitely has a voice for those who can tune in. Hexagon changing color. Saturn's north polar hexagon mentioned earlier isn't static in appearance. Between 2012 and 2016, As the North Pole went from winter darkness into spring sunlight. Saturn's year is 29.5 Earth years. The hexagon region changed from a cool blue tint to a golden hue. Scientists think that during the long polar night, atmospheric gases had settled and cleared, giving a blue transparent look, similar to how Neptune's atmosphere is blue. But once sunlight hit, photochemical smog, haze particles built up in the polar atmosphere, turning it hazy yellow. Essentially, Saturn's hexagon eye changed color with the seasons, possibly due to the increased production of UV-triggered haze in spring. This is startling. A planetary scale structure literally shifted color from one mission to another, suggesting the clear hexagon became foggy. It's an enormous analog to seasonal change. Imagine an entire pole of a planet switching color over a few years. That's what happened on Saturn. It's a reminder that even on giant worlds, seasons matter. For almost a decade, Cassini watched the northern hexagon gradually get mistier and more golden, while the southern pole going into winter possibly started to clear up. These changes were subtle year by year but dramatic over a decade. To any being on Saturn, it would be imperceptible in the short term, but when the data is laid out, it's clear. Saturn's very hues breathe in and out with the passing of its long year. The eerie part is thinking of these massive systems, the hexagon jet stream and polar vortex, operating on such scales of time and space that color itself is a seasonal variable. Saturn truly has golden years and blue years, at least at its poles. The quiet between rings. The space between Saturn's rings is surprisingly empty. When Cassini threaded the 2000 km gap between Saturn's innermost D-ring and the cloud tops on its final orbits, everyone braced for lots of dust hits. Instead, Cassini found an odd calm, virtually no particles in that zone. It was a lucky break for the spacecraft, which oriented its antenna as a shield just in case. The void there was unexpected because models suggested ring material should diffuse inward. This quiet gap, just a few hundred kilometers above Saturn's atmosphere, is almost like a moat of emptiness separating the rings from the planet. Cassini's star tracker saw an essentially pitch-black sky between the innermost faint ring and the atmosphere. This emptiness means that for some reason, perhaps Saturn's magnetic field clearing dust, or atmospheric drag gobbling it up, ring particles don't easily drift all the way down. They get caught or destroyed, leaving a relatively dust-free zone. There's something poetic and chilling about that. One could float in that ink-black gap and look inward at the beige cloud deck of Saturn, and outward at the shimmering wall of rings, and be in a sort of null zone, a gravitational and material lacuna. Of course, you'd also be bathed in Saturn's radiation belt there and speeding around in orbit. But it's arguably one of the most unique orbital zones in the solar system between a giant planet and its rings, and it turned out to be calmer than we thought. This is a stark contrast to, say, the environment near Jupiter's rings. Jupiter's rings are faint, but the radiation there is intense. Saturn's near-field environment was practically serene for Cassini, a last little gift from the planet to the spacecraft that studied it for 13 years. Lightning storms. You can hear across space. Saturn's lightning is so powerful that radio telescopes on Earth can detect the emissions when Saturn's hemisphere faces us. These lightning-generated radio bursts are called Saturn electrostatic discharges, SEDs. During the Great White Spot of 2010 to 2011, Cassini picked up lightning crackles 10 times more frequent than in other storms, indicating an extremely electrically active system. The CD signals received had repetition rates up to a few per minute over long stretches, meaning Saturn was crackling with continual lightning for months. An observer above the clouds might see mile-long lightning bolts flickering almost continuously in some thunderheads, making Saturn's night side occasionally brighter locally. These megabolts can heat air to 30,000 K and create shock waves, essentially planetary-scale thunder. If one could somehow float in Saturn's upper atmosphere, say in a sturdy balloon during one of these storm episodes, they would experience an almost unbroken rumble of thunder, punctuated by blinding flashes that illuminate the rolling ammonia clouds for hundreds of kilometers. It would be terrifying and magnificent. Cassini actually recorded the audio of thunder on Saturn by converting radio waves to sound. It's an eerie crackling static. Knowing that Saturn, often seen as placid and pastel, can drum with peals of thunder more incessant than any Earth supercell, reminds us how deceiving looks can be. Under those seemingly calm cloud bands are storms unleashing energies rivaling small nuclear bombs. Saturn's peaceful appearance is partly a factor of distance and scale. Up close it's a dynamic, even violent place, just stretched over larger areas. So Saturn, the gentle giant with lovely rings, actually hosts storms so wild their thunder could be heard from space, a duality that fascinates and warns us of the power hidden behind beauty. Titan's hidden hand. Saturn's largest moon Titan, with its thick atmosphere, exerts subtle influences on Saturn and the rings. Titan's gravity shepherds some outer ring material, and may be clearing a gap in the E-ring. Titan also plays a role in Saturn's magnetosphere. It's so massive, it creates a void, a Titan-induced gap, in the plasma around Saturn as it orbits, and it can even generate waves in Saturn's magnetic tail by its orbital motion. Titan orbits at 20 Saturn radii, out there among the faint G and E rings, and its dense atmosphere means it's a chemical factory. Complex organics from Titan's upper atmosphere likely escape and rain onto Saturn's magnetic field lines, possibly feeding Saturn's magnetosphere with charged particles. In essence, Titan bleeds some of its atmosphere to Saturn, tiny amounts, but measurable. Also, Titan's gravity over millions of years has forced certain ring particles and smaller moons into resonances. Some gaps in the rings correspond to Titan's orbital period commensurabilities. It's as if Titan silently sculpts some of Saturn's environment from afar. The most haunting aspect, Titan is also potentially habitable in its subsurface ocean or as a site of exotic life, with liquid methane on surface. If Titan harbors life in its lakes or underground, then those life processes producing certain gases could indirectly influence Saturn by altering Titan's atmosphere and therefore its plasma interaction. It's a stretch, but conceivable that microbes on Titan could subtly affect Saturn's giant system via chemistry. In any case, Titan's looming presence, a moon bigger than Mercury, cloaked in orange haze, is another ghostly figure in Saturn's story, a satellite so influential it acts almost like a second planet, shaping the gravitational and plasma environment. Saturn doesn't live in isolation. Titan's there, tugging and breathing, via atmosphere, doing the slow work of cosmic collaboration. This interplay between Saturn and Titan is quiet and invisible to the eye, but it's happening, a moon gently tuning the rings and magnetosphere of its parent planet. Quiet awe indeed. Inconstant day length. Measuring Saturn's rotation turned out to be weirdly difficult, because Saturn is a gas giant with no surface, and its magnetic field is almost perfectly aligned with its rotation axis, unlike Jupiter's. The Saturn kilometric radiation, SKR, basically radio pulses tied to rotation, that Voyager measured in 1980, gave a rotation period of about 10H39 M24S. But Cassini in the 2000s found the SKR modulation had changed to about 10H47 M6S, several minutes longer. Saturn's day seemed to drift by up to 1% per year. The current thinking is that high-altitude winds or the plasma disk are dragging the magnetic field in a way that makes the radio period appear slower. Essentially, Saturn's magnetosphere's heartbeat varies with its seasons. This is unprecedented. A planet whose reported day length can change over time. It's possible Saturn's true rotation is constant, but we lack a stable indicator. Nonetheless, inside Saturn, differential rotation means different latitudes and depths rotate at slightly different speeds. So a day on Saturn is a fuzzy concept. The deep interior might spin at one rate, the cloud zones at others, and the radio emission at another. Imagine being on a planet where even the concept of a fixed day is slippery. One day in the future, if we place a network of sensors around Saturn AG orbiters or atmospheric probes, we might piece together a clearer picture. But it may be that Saturn's day will always be quoted with an uncertainty of several minutes. There's an existential unease in that something as fundamental as a planet's rotation period, usually a fixed number, is elusive on Saturn. It reminds us that Saturn is not a solid body at all. It's a flowing, changing fluid, and our human need to impose a single rotation period is almost an artificial convenience. Saturn resists that simplicity, swirling in differential rotation such that the very idea of day blurs into a band-dependent phenomenon. On Saturn, time as measured by rotation is just a bit less rigid than on a rocky planet. It's a giant slow pulsation instead of a precise tick. A ring rain of organics. Cassini's finale revealed that Saturn's rings are dumping not just water into Saturn but also complex organic compounds, including methane, ammonia, carbon monoxide, nitriles, and nanograins of silicates. Roughly 22,000 pounds, 10,000 kilograms of material per second falls from the rings into Saturn near the equator. This includes a lot of water but also a significant fraction of heavier molecules. In essence, Saturn's upper atmosphere is being enriched by ring matter. This rain likely creates rich auroral ovals in UV, observed as mysterious glowing bands, and may even seed Saturn's cloud tops with dust that serves as condensation nuclei. The rings, which might have originated from a shattered icy moon, are now returning that moon's ingredients to Saturn. It's a poignant cycle. Something that might have harbored organic chemistry, a moon's subsurface perhaps, was destroyed to form the rings, and now its complex chemistry is raining back down onto Saturn to be mixed into the planet. To Saturn, the rings are ephemeral, but as long as they exist, they act like a nutrient drizzle, delivering elements and compounds to the planet. One might poetically say Saturn is eating its rings. The idea that Saturn is inhaling organics from its rings is not just scientific curiosity, it also affects ring evolution, depleting certain particle sizes and compositions faster. It's almost a metabolism. Saturn is digesting its rings gradually. If life ever somehow existed on an icy moon that became the rings, then microfossils or organics from it could now be raining into Saturn. Those would break apart in Saturn's atmosphere, of course, a final dissolution. Saturn's ring rain is thus like a funeral ash being sprinkled onto the planet, where it gets absorbed. This dynamic underscores that even something as seemingly static as rings are in fact interacting continuously with the parent planet. Saturn's appearance of serene permanence belies the truth. It is consuming a part of itself or its system. In a few 100 million years the rings may be gone, but Saturn will carry their ingredients forever in its atmosphere and interior. Tipped on its side. Uranus is an oddity among planets. It's tilted 98 degrees, essentially rolling around the Sun on its side. This extreme tilt likely resulted from one or more titanic collisions during its formation. The consequence is 42-year-long seasons of constant daylight or darkness at the poles. Each pole gets 42 years of unending sun, then 42 years of night. When Voyager 2 flew by in 1986, Uranus's south pole was in full sunlight, and the planet looked like a bland pale cyan orb with very little banding or storms. The sun was almost directly over the pole, driving gentle convection. For decades after, as equinox approached in 2007, Uranus woke up, developing storms and banding as the sun hit the equator. The sheer strangeness of a planet lying on its side cannot be overstated. Near the poles, the sun would circle the sky at the horizon during the brief spring-fall, then climb to zenith for decades of never setting, then slide down and vanish for decades. Near the equator, the sun would rise and fall, but on a wildly different path than on Earth, and half the Uranian year, 84 Earth years, those equatorial regions would have the sun in the northern sky, the other half in the southern sky. Uranus's sideways orientation means extreme seasons and weird weather patterns. It essentially has a lying down magnetosphere too, causing auroras at weird locations not aligned with its rotation. This 98 degrees tilt gives Uranus a unique spooky rhythm. The sun can shine from the north, then from directly above, then from the south, each for decades-long intervals. It's as if some giant knocked Uranus over in a cosmic accident. In a way, Uranus is the solar system's lost soul, spinning the wrong way, retrograde on the wrong axis, bearing the trauma of a massive collision in its very stance. That collision likely not only tilted Uranus but could have scattered its original moons and maybe created a debris disk that reformed into the current moons and rings. so Uranus's whole system may have been reborn out of a cataclysm. The eeriness of Uranus is that it looks placid, yet its entire configuration screams of a violent past. Coldest planet. Despite being closer to the Sun than Neptune, Uranus holds the record for coldest atmospheric temperatures in the solar system. The thermosphere can dip to 124 degrees Celsius 49 K. Uranus seems to emit almost no excess internal heat, unlike all other giant planets. One hypothesis is that the big collision eons ago expelled much of Uranus's primordial heat, or left behind an insulating layer in its interior that prevents heat from escaping. Thus, Uranus's atmosphere is cryogenically cold. At the 1 bar level, it's about 195 degrees Celsius on average. If you were in Uranus's upper clouds, the air would be far colder than Antarctica's worst winter. Methane there condenses to ice crystals, giving the blue-green color. The lack of internal heat also partly explains why Uranus's weather is usually subdued. No strong banding or storms except around equinox. It's a planet in deep chill, seemingly dormant. This makes Uranus scientifically intriguing. Why so cold? But also a bit forlorn. It's an ice giant that truly lives up to the ice name, seemingly having lost the warmth of youth. Some models suggest Uranus may have a cold, unmixed outer layer that traps a warmer interior below. If that layer ever gets disturbed, say by another big impact or intense season, perhaps Uranus could heat up a bit. For now though, Uranus is an almost ghostly cold world with a languid atmosphere barely driven by sunlight, because at 19 AU sunlight is feeble. Neptune, further out, actually has a more vigorous and warmer atmosphere thanks to internal heat, while Uranus languishes. It's as if Uranus is in shock, knocked over and left shivering. The idea that a planet can essentially shut down internally is a sobering planetary fate. Uranus may well be a vision of a planetary coma, alive, rotating, orbiting, but inert in many ways, a giant embalmed by cold. Lopsided magnetic field. Uranus's magnetic field is skewed crazily. The dipole axis is tilted 59 degrees from its rotation axis and offset from the center by a full 1/3 of the planet's radius. This means the magnetic field strength at one pole is over 10 peters stronger than at the other pole. As Uranus rotates, the magnetosphere wobbles asymmetrically, likely causing the magnetic tail to twist into a corkscrew shape behind the planet. The auroras on Uranus are weirdly placed too, not in tidy ovals like Earth, but likely in spots determined by where the magnetosphere intersects the atmosphere. One can imagine the auroras on Uranus sometimes appearing at mid-latitudes or wandering as the field orientation relative to the Sun changes. A charged particle traveling toward Uranus might suddenly find the magnetic field weakening or strengthening drastically as it encounters these offset regions. Some scientists likened it to a magnetic field sloshing back and forth inside Uranus as it rotates. No other planet has such an off-kilter field except Neptune, which is similar though not as extreme an offset. The likely cause is that Uranus's dynamo, the conducting fluid region generating the field, is located in a thin shell of the icy mantle, not the core, due to specific pressure-temperature conditions. It might be inherently unstable or transient. The image of a planet with a drunken magnetic field is unsettling in a way. On Earth, the field gives a sense of orientation and global coherence, but on Uranus, compasses would be utterly confused. If you tried to map out magnetic north on Uranus, you might find two strong North Pole regions in opposite hemispheres and a drastically weaker field elsewhere. It's like Uranus's magnetic heart is off-center, perhaps another consequence of the cataclysm that toppled it. For anyone exploring Uranus, navigation by magnetics would be nightmarish, a truly alien magnetic environment where the field lines might even loop out into space in weird ways before re-entering on the other side. It's a reminder that planetary dynamos can take bizarre configurations. A magnetic field doesn't always neatly align like a bar magnet through a planet's center. Uranus's field is fractured and lopsided, almost as if the planet's very soul was knocked askew. Dark, narrow rings. Uranus possesses a system of thin, faint rings that are charcoal dark, albedo only a few %. Unlike Saturn's broad, gleaming rings, Uranus's rings are sparse and composed of radiation-darkened ice and rock. They were only discovered in 1977, when they occulted a star dimming its light in sharp steps. There are 13 known rings, most just a few kilometers wide. They are so thin and tight that Voyager 2, when it flew by, could barely photograph them. They appear as spidery arcs around the planet. The Epsilon ring, the brightest, is still very dark in absolute terms and has variations in particle size across it. Strangely, the rings likely originated from shattered moons. Perhaps the same event that tilted Uranus also wrecked some inner moons and created a debris disk. Over time, the smallest dust was depleted, swept onto remaining moons or into Uranus's atmosphere, leaving mostly larger particles, which is why the rings are dust-poor and composed of mostly centimeter to meter-sized pieces. When Voyager flew behind Uranus and looked back at the rings, some of them glowed with forward-scattered light, revealing sheets of fine dust that weren't visible from Earth. It implied the rings have strands or arcs of dust that are seen only at certain phase angles. These rings are also not stable on billion-year scales. They probably must be continuously replenished by collisional grinding of moonlets, or else they'd disappear. Uranus's ring system is like a ghost of a once greater ring. It's the bare skeleton, dark and ephemeral. The thought of being near those rings, if you could station keep with a spacecraft, you'd see maybe a very faint band of darkness blocking background stars momentarily, but not the brilliant panorama of Saturn. If you flew through them, you might not even notice a grain hitting your ship, unless you hit one of the larger rare rocks. They are quiet, almost invisible rings, a shadow of Saturn's glory. As Uranus moves through seasons, the ring orientation changes relative to Earth. In 2007, they were edge-on and practically vanished from view. Then as they opened, we saw them again in occultation data, and with Keck's infrared imaging. But to the naked eye, Uranus's rings are too dim to see. They truly are specters, known only to instruments, and likely transient in cosmic time. They lend Uranus a touch of mystery. What else is hidden around an apparently bland planet? Only by clever observation did we even detect these dark rings and the small shepherd moons that accompany them. It's a reminder that the solar system still holds secrets in plain sight that are just really hard to see. Seasonal storms and surprises. For decades after Voyager's flyby, Uranus appeared extremely quiescent. But around 2004 to 2007, as Uranus approached equinox, astronomers observed a rash of bright storms and cloud features erupting in the once boring atmosphere. In 2006, a storm dubbed the 4th of July storm was so bright in infrared it outshone even Saturn's storms. In 2014, after equinox, Keck Observatory spotted extremely large storms. One was 9,000 kilometers across, and even amateur astronomers with good telescopes could see faint white spots on Uranus's blue-green disk. One might say Uranus went from pale aqua cue-ball to showing visible banding and spots. This was surprising given its lack of internal heat. Possibly, as the equatorial regions got more solar heating, latent heat stored deep down percolated up, or the sheer change in insolation patterns stirred the atmosphere. The planet that was long called bland was revealed to have a dynamic weather cycle on a decades-long period. It's just that we weren't watching long enough. Now we know that when the sun rises on Uranus's equator, after 42 years of polar day-night extremes, it triggers convective storms, some of which might be akin to thunderheads or massive methane cloud upwellings. The spooky part is, if any future explorer drifted in Uranus's atmosphere during the long winter, they'd see a calm sky with maybe faint high clouds. Then as the sun angles change, out of nowhere enormous methane storm cells could erupt, potentially with hail of methane or ethane raining down. These storms can reach high altitudes where they reflect sunlight brightly, hence their visibility. And then after some years they might subside again into the background haze. Uranus's heartbeat is one of bottled-up energy releasing rarely. It reminds us that even the most sluggish-looking planets can surprise us given time. There's a bit of forlorn sadness in it too. We glimpse these storms via telescopes, but no probe has been there since Voyager. We saw Neptune's weather up close only once, for Uranus never since its quiet phase. By the time we send another mission, maybe in the 2030s or 2040s, Uranus will be heading towards solstice again, perhaps calmer. We miss the big show up close. It's a lesson in patience and the grand timescales of outer planet meteorology. The planets have moods that last longer than human careers, but not longer than human curiosity. We'll watch from afar, aware now that Uranus is not a static ice ball but a sleepy giant that occasionally stirs. Radiation and rings that glow in the dark. Uranus's radiation environment is milder than Jupiter's or Saturn's but still present. The planet's magnetic field traps charged particles, and interestingly, when Voyager passed through the plane of Uranus's rings, it detected ring shadows in charged particle counts. Basically, the rings block some radiation, creating gaps in the distribution. Those findings hinted that Uranus's main rings have almost no dust. Dust would let radiation through, consistent with their particle-starved nature. Moreover, those energetic particles hitting the rings likely cause chemical reactions and glow. In 2017, researchers using thermal imaging found Uranus's rings surprisingly bright in millimeter wavelengths, suggesting they are unusually warm or have special thermal properties, possibly due to energy deposition by radiation. It's been hypothesized that Uranus's rings, especially the epsilon ring, could faintly glow in optical if you were nearby, not from reflected sunlight, but from luminescence of charged particle hits or faint thermal radiation. If one orbited Uranus in darkness, say, on the night side with the sun blocked by the planet, perhaps they'd see a tenuous ring shine, extremely faint, like a pale ghostly band encircling the planet. Combine that with Uranus's auroras, dim but detected by Voyager's UV instrument, and you have a rather haunted scene. A sideways planet in darkness with thin whispery rings that barely glow and off-kilter auroral patches flickering on its globe. It's a far cry from Saturn's vibrant reflective rings and bright auroras. It's the shadow version of that. One could almost anthropomorphize Saturn bright and gregarious, Uranus 87. Supersonic winds. Neptune holds the record for the fastest winds of any planet. Jet streams on Neptune can roar at 2,100 km per h, 1,300 miles per hour, far exceeding the speed of sound. These winds drive Neptune's large storms, like the Great Dark Spot, around the planet. Such velocities are astonishing given Neptune receives only 1/900th the sunlight Earth does. It indicates Neptune's atmosphere is powered by a significant internal heat source. Neptune emits 2.6 times more energy than it gets from the sun. In Neptune's roaring winds, frozen methane clouds race through the frigid air in a blur. If you were in Neptune's upper atmosphere, you'd see clouds streaking by at Mach 2. Yet, oddly, because the air is so thin, a 1,300 miles per hour wind might exert only as much force as a gentle breeze on Earth's surface. It's a strange thought, supersonic gusts that you might not even feel directly, yet they carry enough momentum to encircle the planet in mere days. Neptune is an almost silent storm world, where the winds are ferocious but the whisper-thin air gives them an insubstantial quality, a terrifying speed married to an extreme cold calm. Great Dark Spot. Here 1 decade, gone the next. When Voyager 2 flew by Neptune in 1989, it discovered a gigantic storm, the Great Dark Spot, an oval tempest roughly the size of Earth, raging in Neptune's southern hemisphere. Yet when the Hubble Space Telescope looked for it in 1994, the Great Dark Spot had vanished. In its place, Hubble later saw new dark spots in Neptune's northern hemisphere. Unlike Jupiter's Great Red Spot centuries old, Neptune's great storms appear and dissipate on timescales of just years. It's as if Neptune's atmosphere erases its colossal storms regularly. The Great Dark Spot likely dissolved into smaller storms or was blanketed by high-altitude methane clouds that Voyager saw as bright companion clouds along the spot's edge. Currently, Neptune's southern hemisphere has no large dark vortex, but recently, 2018, a new Great Dark Spot formed in the north, detected by Hubble. These dark vortices are transient, coming and going with Neptune's seasons. Their impermanence is unsettling. A vortex large enough to swallow continents can just fade away into nothingness within a few orbits of the Sun. Neptune shows us a planetary atmosphere in a state of constant change, where even the mightiest storm leaves barely a trace. One season Neptune's face can be scarred by an Earth-sized cyclone. A few years later, it's gone without a scar, a ghost in a supersonic wind. Diamonds in the deep. Deep within Uranus and Neptune, scientists suspect it rains diamonds. The great pressures, millions of atmospheres and high temperatures in their mantles can break hydrocarbons like methane into carbon, which then crystallizes into diamonds that literally precipitate like hail. Laboratory experiments have shown that under Neptune-like conditions approximately 6,000 K and 6 GPa, diamond formation is indeed possible. So far beneath Neptune's blue clouds there might be a glittering rain of solid diamonds falling for thousands of kilometers until melting into liquid carbon in hotter layers. These diamond rain predictions give an almost fairy tale image to Neptune's otherwise steely science, an unseen storm of jewels in permanent darkness. It's haunting to imagine. No human will ever witness it directly, but those diamonds may collect around Neptune's core over billions of years, perhaps forming a layer of slushy diamond ice. In the far future, some interstellar mining operation might covet Neptune's deep treasures, but for now it's a hidden facet of the planet's nature. The idea that Neptune's deep interior might glitter with unearthly diamonds adds to the mystique of these distant ice giants, turning them into cosmic alchemical labs where common gas is transmuted into precious crystal, only to vanish into the depths. Off-kilter magnetism. Much like Uranus, Neptune's magnetic field is bizarrely oriented, tilted 47 degrees from the rotation axis, and offset by about 55% of Neptune's radius from the planet's center. This means Neptune's magnetic field is lopsided and asymmetric. As Neptune rotates, its magnetic field swings around like an off-center bar magnet, causing the auroras to wander in latitude and the magnetic tail to twist into a corkscrew shape behind the planet. Voyager 2 observed auroral flashes in Neptune's atmosphere, but they were not aligned in neat ovals as on Earth, likely because of this wonky magnetic configuration. Neptune's magnetic poles don't coincide with its geographic poles. If you tried using a compass on Neptune ignoring the logistical impossibility, it would point toward a spot in the far southern hemisphere, nowhere near the actual pole. This strange dynamo likely arises from Neptune's internal structure. The dynamo currents flow in a shell of ionized water-ammonia ocean in the mid-mantle rather than in a central core, producing a cloverleaf field rather than a dipole. The result is that Neptune's northern hemisphere experiences a much stronger magnetic field than the southern hemisphere. It's almost as if Neptune has a magnetic north pole in the northern mid-latitudes and a south pole near the southern pole, but offset, making the field strength uneven across the planet. This could lead to peculiar space weather. Charged particles might crash into Neptune's atmosphere at unexpected latitudes, creating brief auroral glows randomly across the globe. Neptune's skewed magnetism reminds us that the orderly bar magnet model of planetary fields has wild exceptions. It feels like a planetary broken compass, a magnetic field that bears scars of Neptune's formation conditions. It's another Neptune mystery, a deep interior that generates a topsy-turvy magnetic veil, unseen but powerful. Triton, captured and condemned. Neptune's largest moon, Triton, is a strange world moving in a retrograde backwards orbit. This indicates Triton was likely a captured Kuiper Belt object, not born with Neptune. The capture of Triton was a violent event. It likely caused Neptune's original satellites to be perturbed or destroyed. Today, Triton is gradually spiraling inward due to tidal interactions. In about 3.6 billion years, Triton will reach Neptune's Roche limit and be torn apart, potentially forming a spectacular ring system like Saturn's for a time before raining down onto Neptune. In the present day, Triton is geologically active. Voyager 2 saw nitrogen geysers spouting from its surface and a thin nitrogen atmosphere with hazes. It's one of the coldest active worlds known, approximately 38 K. If any microbes existed in Triton's possible subsurface ocean, their home will eventually be ripped to shreds and spread around Neptune as ring material. Triton's fate is sealed. It's a doomed moon. For now it orbits Neptune every approximately 5-9 days, retrograde, inclined -23 degree. It has cantaloupe-like terrain and black smoker's dark plume fallout deposits near its south pole from the geysers. It's likely a twin of Pluto captured into bondage. The emotional gravity of Triton's story is heavy, a wayward world caught by Neptune's gravity forced into a retrograde dance that will ultimately destroy it. In a sense, Neptune will consume Triton, first by breaking it into a ring. Neptune's own rings are currently scant and dark, but Triton's breakup would create a dazzling new set, and then by pulling that debris in. Neptune has already tidally locked Triton and stripped away Triton's original companions. In time it will shred the moon itself. This dark future echoes what happened to Uranus's moons that likely formed its rings. In the cosmic balance, big planets take a deadly toll on captured moons. Triton's orbit is the harbinger of its demise, and Neptune's gravity, though currently imparting geyser energy via tides, will one day be Triton's executioner. For now, we watch a dynamic equilibrium. Triton's geysers hint at an internal warmth likely fed by tidal kneading, the same forces dragging it down. It's a chilling example of a planetary system's unforgiving mechanics. Ring arcs and dusty rings. Neptune has a set of faint rings, much more tenuous than Saturn's, and curious clumpy ring arcs in its outer Adam's ring. These ring arcs, named libertaire, égalitaire, fraternitaire, confounded scientists because orbital mechanics dictate that ring material should spread out evenly, yet these arcs remain concentrated. They occupy about 10 to 20% of the ring's circumference and have persisted at least since Voyager 1989 to ground-based observations in the 2010s. It's thought that the moon Galatea, just inside the Adam's ring, and possibly self-gravity among arc particles help corral them. But the arcs may still slowly drift or evolve. The arcs are extremely faint. Voyager needed long exposures and the right viewing geometry to detect them. If you were floating just above Neptune's equatorial plane, you might see the arcs as slightly brighter segments in an otherwise ghostly diaphanous ring. Neptune's rings in general are dusky and small particle-rich compared to Uranus's or Saturn's. The densest, Adam's ring, is only ~5 e6 kg in total mass. That's a trillion times less massive than Saturn's rings. These rings are likely short-lived. Perhaps they formed when Triton's capture shattered a pre-existing inner moon system, creating debris that slowly cleared except for these last vestiges. They have peculiar chemistry too. Voyager saw that they contain unusually dark material, carbon-rich. In recent years, when observed at microwave wavelengths, Neptune's rings glow more than expected, implying abundant tiny dust grains that warm slightly in sunlight and re-radiate. Possibly, Neptune's rings have a higher fraction of dust than Uranus's, thanks to Triton's perturbations constantly grinding ring particles. The ring arcs themselves could be clumps of dust and ice that are self-gravitating enough to resist dispersion, or are corralled at a 42-43 resonance with Galatea. Their existence speaks to the delicate balancing act. Neptune's rings are on the edge of disappearance, and the arcs might be the last stage before the ring breaks into discrete moonlets or dissipates. In a way, we might be catching Neptune's rings at the tail end of their life, or perhaps at the beginning, if Triton will eventually feed them more. They are a flicker, an intermediate between a full ring and a moon. Looking at the arcs is like seeing a ring in the process of quantizing into moonlets or vice versa. It's another reminder of how dynamic and temporary ring systems can be outside of Saturn's massive example. Moons in chaos. Neptune's inner moons, Naiad, Thalassa, Despina, Galatea, etc., to have a crowded, chaotic dance. Naiad and Thalassa are in a unique, resonant ballet. Naiad's orbit is tilted, and it bobbles up and down, passing Thalassa in a 73-69 resonance. Every time Naiad laps Thalassa, it is at a different phase of its inclined orbit, so that it always passes safely when Thalassa is below, avoiding collision. This weird orbital resonance, discovered with Hubble and confirmed by recent analysis, is sometimes poetically called the dance of avoidance. It's as if the moons choreograph their orbits to never meet. Despina and Galatea are likely in unstable orbits that in long term may lead Despina to eventually hit Neptune's rings or Galatea. In fact, Despina may be slowly migrating inward and could collide with the Leveria ring or eventually Neptune itself. The orbits of these small moons are strongly influenced by Triton's gravity and Neptune's higher-order harmonics. It's a dynamically active system, not a placid one. If one could speed up time and watch from above Neptune's north pole, one might see these inner moons executing intricate loops, sometimes catching up to each other and then veering due to resonances, a true gravitational dance. Some might swap orbital energy, shift slightly, or get perturbed by ring material. Neptune's inner moon system feels unsettled, likely due to Triton's capture wiping out the original regular moons. What we see now are either fragments of that old system or new clumps coalesced from debris. They have not had enough time to reach a long-term stable configuration. That is a bit haunting. Neptune's inner moons are survivors in a post-cataclysm environment, still sorting out their lives. The fact that some of them, like Naiad and Thalassa, found a special resonance to avoid each other hints at possibly many others that weren't so lucky and may have collided in the past, creating Neptune's dusty rings. It's celestial mechanics in action, showing us a system in flux. Over millions of years from now, some inner moons may fuse or break or spiral down. We happen to be observing Neptune's moons mid-chaos. It's rare by contrast. Saturn's inner moons are fairly locked in resonances or stable gaps. Neptune gives us a glimpse of the aftermath of planetary violence, a reconstructed moon family still figuring out their gravitational relationships. In that sense, Neptune's inner reaches are a crime scene, and the moons and rings are forensic evidence. Pluto's cousin, Triton, is often called Pluto's twin, similarly large, approximately 2,700 km, icy, with nitrogen atmosphere and surface. It likely came from the Kuiper belt. When Neptune snared Triton, Neptune essentially stole a dwarf planet. This event might have been billions of years ago, yet Triton still has internal heat, evidenced by cryovolcanism. Perhaps the capture and subsequent tidal evolution heated Triton's interior, enabling a subsurface ocean that persists today beneath the crust. If so, Triton could potentially harbor life in that ocean, making Neptune indirectly a host to life. If any microbes swim in Triton's dark ocean, they are utterly cut off from the rest of the solar system, under approximately 30 km of ice, around a planet they didn't form with, orbiting retrograde. It's a science fiction scenario, a habitable zone within a captured world. Triton's surface also shows evidence of refreshing, very few craters, lots of young terrain. Pluto, by comparison, also has a young heart region, Sputnik Planitia. It's compelling that the only two Kuiper belt dwarf planets we've seen up close, Pluto and Triton, were geologically active. It implies many large KBOs are not inert ice balls but dynamic worlds. Neptune happened to capture one, giving us a front-row seat via Voyager to a KBO without sending a spacecraft to 30 AU. We saw geysers spurting on Triton, dark streaks from nitrogen eruptions carrying dust aloft approximately 8 km. Standing on Triton's frozen flats, you'd see the faint sun about 30 times smaller than from Earth, and perhaps on the horizon, a thin misty plume rising and drifting with the wind, casting a long shadow on the pinkish nitrogen ice. Overhead, Neptune would loom 15 degrees across, a huge bluish-green orb filling the sky. Triton is only approximately 355,000 km from Neptune, far closer than our moon is to us. To Triton's hypothetical microbes, that blue orb is their sun and moon combined, the source of tidal energy keeping their ocean liquid. But that relationship is fatal in the end. Triton's story is a tragic tale of a world that might have thrived orbiting the sun, now condemned to orbit a planet, and eventually be torn apart by it. It's a cautionary tale in celestial mechanics of how one world's gain, Neptune's big moon, is another world's existential crisis. Neptune's disappearing atmosphere. In recent decades, ground-based telescopes have observed puzzling changes in Neptune's stratospheric temperature. From 2003 to 2018, Neptune's global average stratosphere cooled by about 7 degrees Celsius. Then from 2018 to 2020, the South Pole's stratosphere rapidly warmed by 11 degrees C. This may be a seasonal effect. Neptune's southern hemisphere had been in summer and now heading toward autumn. Neptune's year is 165 Earth years, so seasons last approximately 40 years. Still, models didn't predict such a swift change. It hints at unknown dynamics in Neptune's upper atmosphere, perhaps linked to changes in photochemical haze or unexpected atmospheric circulation shifts. If the trend continued unabated, unlikely, one might worry about Neptune's ability to retain certain gases. Of course, Neptune won't lose its atmosphere entirely like that, but it shows how even at the edge of the solar system, climate cycles and variability are present, just on very long scales. Neptune's energy balance is not fully understood. There's a solar energy crisis wherein upper levels are warmer than expected, and a flux crisis where internal heat is significant. The recent cooling might indicate that as Neptune's south pole receives less UV sunlight post-solstice, certain hydrocarbons condense out, causing radiative cooling. Then the polar warming post-2018 might be due to regional changes or some delay in seasonal response. It's as if Neptune is breathing out and in as it goes through equinox. These discoveries make the serene blue Neptune more dynamic and somewhat unpredictable. It's not a static, perpetual, steady-state ball. The climate of Neptune has mood swings we are only just noticing now that we have decades of data. It serves as a humbling reminder. Our snapshot from Voyager 2 was just that, a snapshot. Planets, even far-flung ones, change with time. Some changes are cyclical, others could be anomalies. Without sustained observation, we might misinterpret a planet's true nature. Neptune teaches us patience in planetary science. The living sky of even an ice giant is a complex, time-varying phenomenon. No space for spacecraft. The 1989 Voyager mystery. As Voyager 2 approached Neptune in 1989, it carried with it the lessons of Saturn and Uranus encounters. At Uranus, it had sailed relatively safely through the equatorial plane near the rings without issue. At Neptune, mission planners were wary of dust in Neptune's ring plane potentially threatening the probe. The trajectory was adjusted to pass over Neptune's north pole at closest approach, about 5,000 kilometers above the cloud tops to minimize time near the ring plane. During the flyby, Voyager detected fewer dust impacts than expected, implying Neptune's rings are indeed very low density. Nonetheless, during the closest approach, an unexplained quirk occurred. Voyager 2's instruments recorded a delay in the expected arrival time of its radio signal by a few seconds. At first, there was panic that Voyager grazed something or was off course. It turned out to be a relativistic timing correction error in predictions, but for a moment engineers thought Neptune's gravity or some unknown factor had altered the craft's trajectory unexpectedly. It was a fleeting scare of the unknown, fitting for the last planet of the classical solar system. Ultimately, Neptune graciously let Voyager through unscathed, and with that, no spacecraft has visited Neptune since. Neptune remains out there, largely unmonitored except by telescopes. It's strange, we have high-def continuous monitoring of Jupiter and Saturn via orbiters, glimpses of Uranus, Neptune only via Voyager in the 80s, and then grainy telescope data. Neptune especially sits in a kind of observational loneliness. This distance and infrequent observation lend Neptune a permanent mystique. We see weather changes but only from afar. We infer diamond rain but cannot confirm. We detect anomalies, like the ring arcs, and still debate their nature. Neptune is like a book with the first and last chapters read formation and current state, but the middle chapters, its day-to-day intricacies, are largely skipped. As we dream of sending an orbiter perhaps in the 2030s or 2040s, Neptune keeps its secrets a bit longer. It feels lonely out there since Voyager 2 left in 1989. Not a single man-made object has come near. For 33+ years and counting, Neptune and Triton have circled the Sun unvisited. their dark rings whispering into the void, their storms forming and dying unseen except by distant eyes, their moon Triton quietly geysering under a dim sun. Neptune is the last sentinel of the solar system, outwardly tranquil but inwardly complex, waiting patiently for when we muster the will to return and listen to its tale in full. The unknown beyond. As Neptune marks the outer boundary of the planetary solar system, it also guards the gateway to the Kuiper Belt and Oort cloud. Perturbations by Neptune are what often nudge comets from the Kuiper Belt inward. In fact, no spacecraft has yet gone beyond Neptune's orbit with functioning instruments focused on the solar system. Voyager 1 and 2 went onward, but now look outward. So Neptune, in a sense, represents the frontier we've reached. Beyond it lies mostly mystery. The region just beyond Neptune is populated by the so-called scattered disk objects, icy bodies in erratic orbits. Neptune's gravity, along with the other giants, sculpted this population. Occasionally, one of those distant bodies falls sunward, becoming a long-period comet gracing our skies. In Neptune's gravitational influence extends far. It is responsible for Pluto's 3-2 resonance. Pluto never collides with Neptune due to this dance. It likely ejected Triton's original partner, if Triton was once a binary like Pluto-Charon. As the last major planet, Neptune's existence shaped the architecture of the outer solar system drastically. If Neptune hadn't existed, the Kuiper Belt might have an Earth-mass world or two. Instead, Neptune's migrations and resonances cleared much of that material. Neptune thus looms large in the story of solar system formation, yet from Earth's perspective, Neptune was discovered only in 1846 via mathematics and telescopic confirmation, after a mysterious deviation in Uranus's orbit pointed to its presence. In that sense, Neptune was the first planet found by science rather than by eye, a beacon of the intellect. It's poetic that this mathematically predicted planet then became the edge of our known planetary system, and now beyond it we predict again mathematically the existence of a possible planet 9 far beyond. Echoing Neptune's own discovery, Neptune may yet be overtaken in the planetary census by a hypothetical planet 9, but until that is confirmed, Neptune stands as the furthest known planet from the Sun. Its serene blue face is a reminder that even at the extremes of our Sun's influence, worlds can be active and complex. When Voyager 2 turned back after its flyby, it captured a haunting portrait, Neptune as a tiny crescent with the Sun far behind. The last such image of a planet on Voyager's grand tour. Neptune receded into darkness, and with it the solar system's grand parade of familiar worlds ended. It signaled both an end and a beginning. Beyond Neptune lies the interstellar gulf. Neptune's is the cosmic shoreline of our solar archipelago, past it the ocean of stars. In that Voyager portrait, Neptune's crescent is razor-thin, almost disappearing, a ghostly smile in the void. It's a fitting endcap to our planetary neighborhood, beautiful, distant and a bit melancholic in its isolation. We yearn to return, and someday we will. Until then, Neptune drifts along, a magnificent enigma at the edge of sunlight. Auroras at the edge. Neptune also has auroras. Voyager 2 detected faint auroral emissions in the ultraviolet. However, due to Neptune's weird magnetic field tilt and offset, these auroras don't form symmetric rings like Earth's. Instead, they likely appear as diffuse patches that rotate with the off-center field. During the Voyager flyby, a brief surge of UV brightness near Neptune's limb was interpreted as an auroral flare. On Earth, bright auroras are common near poles, but on Neptune, a Voyager might see a gentle purple-green glow materialize at an unexpected latitude, then fade quickly. It would be a subtle phenomenon. Neptune's auroras are hundreds of times fainter than Jupiter's. They might be mostly invisible to human eyes, only detectable with sensitive instruments. Still, the physics is intriguing. Even in the dim reaches at 30 AU, the solar wind and magnetospheric interactions can spark auroras. It ties Neptune to the Sun in a tangible way. A solar storm launched from a flare on the Sun 6 months earlier can eventually cause a fleeting aurora on Neptune. The vast distance and time delay emphasizes how the Sun's influence threads out to even the furthest planet. albeit weakened and rare. Neptune's auroras may also get contributions from Triton. As Triton orbits retrograde, it plows through Neptune's magnetosphere and could create auroral footprints or distort field lines, similar to how Io causes auroral spots on Jupiter. Though Triton's interaction is different due to the orientation, we haven't confirmed such effects, but given Triton's conductive atmosphere, it's plausible some coupling exists. If so, Neptune and Triton form a smaller analogue of Jupiter-Io electrodynamic coupling, with perhaps faint UV glows on Neptune where field lines connect to Triton's ionosphere. It would be another unseen link between planet and moon in this system. For now, Neptune's auroras remain one of the least observed in the solar system. Just brief hints. They remind us that even the coldest worlds have a spark of the sun's energy dancing in their skies occasionally. Plunge into oblivion. Only once has humanity touched the atmosphere of Neptune. When Voyager 2's science package and its discarded upper stage entered Neptune's gravitational sphere, technically some tiny bits of hardware likely ended up on a one-way course into Neptune. After the flyby, Voyager itself went on to interstellar space. But imagine if a probe like Galileo at Jupiter were sent deliberately into Neptune's atmosphere to gather data. The probe would experience a freefall through the highest wisps, just methane haze, then crush through the top of Neptune's troposphere at about 120 degrees, and falling. It would encounter the bright methane ice clouds around a few hundred millibars, likely appearing as thin cirrus. Deeper down a few bars of pressure, it might pass through ammonia and hydrogen sulfide ices. Less is known about Neptune's cloud layering, but by analogy with Uranus and models, the sky above would deepen from bright blue to a dull ultramarine to black as sunlight dims. Pressure rises, temperature climbs. At around 50–100 bars, it's near 0 degrees Celsius. Possibly an ocean-like layer of supercritical fluid forms here. Water, ammonia, ice, melted by pressure. By 10,000 kilometers in, it's thousands of degrees and the probe is long vaporized, its remains joining Neptune's mantle as new constituents. Neptune's atmosphere likely has regions of inertia, gravity, waves, and turbulence. Voyager saw wavy cloud patterns around the Great Dark Spot indicative of atmospheric waves. A falling probe might detect sudden oscillations in pressure or temperature due to these waves, essentially Neptunian weather jostling it until it succumbs. As of now, no such probe exists in our plans, making Neptune's deep atmosphere one of the least sampled. We glean what we can from spectrometry and occultations, like watching how Neptune's atmosphere refracts starlight as a star passes behind it. Voyager 2 did this and measured a temperature profile down to approximately 0.5 bars. Those profiles show a tropopause around 50 K at 0.1 bars, and warming to 60–70 K by 1 bar. Then we largely extrapolate downward. In some sense, Neptune's atmosphere below the clouds is the most physically untouched of the gas giants. Jupiter, Saturn, Uranus all had direct or at least indirect via remote sensing more extensive sampling. Neptune's internal structure remains less constrained. It stands as a frontier for future exploration. An atmospheric entry probe into Neptune would yield enormous scientific value, revealing how ices and fluids behave under extremes, how Neptune's weather and chemistry operate. Until then, Neptune's deep atmosphere remains a dark abyss we've only skimmed. It's humbling that the best we can do is drop our imagination and models into those depths and speculate. One day, hopefully, we'll do it for real, and Neptune will give up another piece of its puzzle. Elegy of the Far Worlds. With Neptune we close the known planetary roster. Its cerulean hue and dynamic climate, Triton's geysers, Uranus's tilt and Neptune's winds, all these underscore that the outer solar system is far from static or simple. Instead, these giants are mysterious, active, and in some cases ephemeral in their features. They also mark the transition to the vast comet reservoirs beyond. Neptune's gravity has sent countless comets into the inner solar system. Without Neptune and Jupiter, Earth would suffer far more impacts. In that sense, Neptune is a distant guardian, as well as a perturber. It's intriguing that the first planet discovered by mathematical prediction became the last planet in our classical lineup. and now another predicted planet, Planet 9, might lurk beyond. The tradition of discovery marches onward. As we reflect on this list of eerie facts and theories from Mercury to Neptune, a theme emerges: each planet is a world of extremes and surprises. From Mercury's double sunsets to Neptune's vanishing storms, our solar system is endlessly wondrous and a bit menacing in its obscure corners. Even excluding Earth, the 7 other major planets offer enough quiet awe and existential unease to fill volumes. Perhaps late at night, under a starry sky, one might look up and ponder Mercury locked in Sun's embrace, or envision Venus's acidic twilight, or Mars's ghost rivers, or Jupiter's raging heart, or Saturn's hexagonal mystery, or Uranus's tipped solitude, or Neptune's transient dark whirls, and feel both inspired and small. These facts are more than curiosities. Collectively, they whisper the story of how rich and eerie our solar system truly is, from the blazing furnace at its center to the cold frontier at its edge. Each planet in its own way teaches a final lesson: there is much we don't know, and even what we do know can unsettle us. That sense of cosmic mystery and humility is perhaps the ultimate takeaway from exploring the planets, and it will beckon us to keep exploring for centuries to come.